Welcome to APEC. It's January 18th, 2025, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on this call, along with everyone watching us on YouTube. Haslen Back is going to do a presentation on Catalyzed Fusion and LENR Energy. Mike McCulloch is going to discuss observations of thrust from Quantized Inertia. And Shiva Meucci is going to be talking about a new solution for deriving the fine structure constant from first principles in Aether theory. We're also going to be hearing some lab updates from our partners and finishing off the event with an open discussion by conference attendees. So a couple of quick updates before we begin. Today's event is using StreamYard. We are broadcasting through the Propulsion YouTube channel. We are also live streaming through several social media channels. If you haven't subscribed, please subscribe to the Propulsion YouTube channel. You can ask questions using the live chat feature on the right-hand side of the page. We do go through those. We try and ask them to the presenters depending on time constraints, but we're not always able to. And I should mention that you can view conference replays, details, and speaker info on our website at altpropulsion.com. So again, 2025, this is our first webinar conference of the year. I cannot express how excited I am. There is so much theoretical and experimental work, especially experimental work, happening in our community. And this is all because of you guys. This is because of the hardworking people who are taking ideas and turning them into reality. I mean, there are 7 or 8 experimental projects that come to mind that some of these have gone farther than anyone has ever dreamed like possible, right? And then others are brand new for the first time. So it's so exciting. So anyhow, without any further ado, let me bring Haslen Back in. Haslen, welcome, sir.
Hi, Tim. Thank you for having me on the show.
Oh, absolutely. Well, and thank you for doing a presentation for us. So let me put your slide deck up. And again, you can use the back and forward buttons in the slide share to go through this. And so what I'll do is take myself out of the studio. I'll be here, but you won't see me. And so why don't I do that? And if you have any issues, you need any help, just let me know.
Tim, I have one question, which is the Q&A. Is there a Q&A at the end, or is it just going to finish as it is?
We can do brief Q&A. StreamYard does not allow, it's not an open forum, like, so we can do Q&A from chat, right? But
yeah, no worries.
Yeah.
Okay. Thanks very much. Well, I'll try and take 1 hour. Is that my scheduled time, isn't it?
Yes, sir.
Okay, I'll stop what's going on now.
Thank you. Okay, brilliant. So I will be here. And again, thank you so much. LENR is something that we have kind of neglected, I guess. That's an area that a lot of our members, a lot of our, like, the people who participate have a massive interest in. And it's something that we haven't touched on that much in the past. So thank you so much.
Thank you. I've shared this for all the CM, condensed matter and nuclear sciences, the low energy nuclear reaction and the cold fusion groups. So hopefully that'll be interesting for them too. Well, good evening, everyone. My name is Haslen Back, as it says on the screen. I'm presenting here tonight on behalf of ENG8, sort of energy with an infinity sign on it. So it's infinite energy. That's what it sort of stands for. And we have been in business for about 7 and 8 years now. That's as a company. The scientists that we've basically partnered with, they've been in business for at least, or they've been experimenting for at least a decade, each team. So we've got 3 labs. Each team has been going for over a decade. The oldest team, 30 years, then about 15 years, then 10 years. And that was before we came in 7 years ago. So it's a very deep tech. And I'm trying to present tonight, not just on ENG8, but I'm going to try and give everyone an overview of what I call catalyzed fusion. It's really known as low energy nuclear reactions. And there's a whole small industry starting on low energy nuclear reactions. And it's previously been known, one might use the word cold fusion, although cold fusion got a bad rap from for various different reasons, the experiments couldn't be replicated, etc. So, but it's an old science. So, what I'll do is I'll go through my slide deck and I'll just explain it. There are a lot of notes in the slide deck because I thought people who are really interested can actually read the notes afterwards. So hopefully it's a good informative update of where LENR catalyzed fusion is at the moment. And I'll explain why we use the term catalyzed fusion during this presentation. Well, people have heard about hot fusion. Billions has been going into hot fusion. You may have read the big Aether program in the European Union. Billions has gone into, let's call them startups, billion-dollar startups, which is in the hot fusion area. And it's around a conjunction which is being proved a couple of times on Earth, sadly, which is the fusion aspect of bonds. And that's the theory that hot fusion is a future source of energy for mankind. But it may be, but I'll explain that there might be something far more readily available and working now on the doorstep. Tokamaks are what happens, are the devices that are required to create a hot fusion device. So the theory is the center of the sun is very hot, it's very high pressure, and scientists have been trying for a very long time to create these reactions actually in laboratory environments or at Aether, huge machines in different parts of the world, the UK's JET program, etc. The biggest difference I try to point out often between catalyzed fusion and hot fusion is catalyzed fusion actually works and can be replicated in laboratories and is going commercial in a number of companies at the moment. So these are reactions that are repeatable, demonstratable, in service, in use in a number of companies at the moment. Whereas hot fusion is a huge bet. In the next 5 to 25 years, companies are trying to get these very complicated tokamaks to actually run and be operational. And they're very expensive. There's no supply chain for them. They require tritium, and there is probably about 3 or 4 kilograms of spare tritium on the planet at the moment. There are some plans to try and harvest more tritium, but it mainly comes off the top of nuclear warheads. So there's an issue regarding the fuel for tokamaks, plus the amazingly complicated engineering to actually produce a tokamak in the first place. Whereas what we'll see during this presentation is that catalyzed fusion reactors or LENR reactors basically are produced from pretty much common garden materials using very low, relatively low tech processes. So, and they're very scalable as well, which I'll go on to show you. Now, the interesting thing is the hot fusion guys are saying that the energy is coming out of the sunshine from the sun, and that sun you see, the surface of the sunshine is around 6,000 degrees Kelvin. That is actually not very hot considering the temperatures and pressures inside the sun. So by the time the temperatures and pressures got to the outer surface, you're seeing about 6,000 degrees Kelvin. Now, when you look at the solar corona, 1 million miles away from that, or past 2 million kilometers away from it, you're seeing that there's 1 million degrees centigrade. It gets hotter and hotter as you go further from the sun and gets cooler as you go towards the surface of the sun. So it's quite an interesting area. And this area is a plasma zone. And there's a beautiful book that's just been written recently. It's called A New Science of Heaven. And despite the slightly esoteric name on that, it's a fantastic book on the science of plasma research that's been done on the planet. And what we're seeing is that this corona, this plasma space, is full of what one might consider to be condensed plasmoids. It's a name for huge concentrations of electrons, negative particles. So to no ado, I'll go on and I'll explain what catalyzed fusion is all about on low energy nuclear reactions. So catalyzed fusion means we basically have a fusion reaction. Why is it a fusion reaction? Because we are doing a number of things. Primarily, we're taking hydrogen, ionizing it, so we've got protons. We're basically combining electrons with protons to form what they call slow neutrons. And then we're adding other protons to it, so we're able to create helium, and we're able to go up the periodic table to carbon. So it's a fusion process. It's been demonstrated since the 1920s. The famous professor J.J. Thomson was a British professor. He was demonstrating that in a small hydrogen reactor, you could create helium back in the 1920s at London College. So this is nothing new, and there have been dozens of tests and experiments to show that basically this is a very semi-common garden pathway. Now, as low-energy nuclear reaction pathways are being studied, there's a different pathways. It's not just one pathway, there's numerous pathways. And I'll go on to explain that. This emerging technology is really gaining momentum at the moment. The Americans, with their APEC energy program, have issued, I think, 10 million of grants to 8 or 10 universities, consortium, to basically work more on their theory, whereas the European Union, it issued has a program called the Clean Hydrogen Metal Energy Program that has shown that you get at least 10 times more energy out of a low-energy nuclear reaction than you do a chemical reaction. And those results were presented in Strasbourg in September last year. Japan has got a very big program going under the auspices of a company called Clean Planet in Japan. And that is also funded by leading companies like Nissan, Toyota, and Mitsubishi. So these are not like garage operations. This is quite big. ENGH itself has got 4 laboratories, including I'm sitting in one of the parts of the lab behind me with a couple of reactors that I'll show you videos on later in my presentation. So it's generally known that if you create some electricity and you want to transform it from a high voltage to a low voltage, the systems can be from 50 to 90% efficient. So if you've got a low energy nuclear reactor and you're creating more than 2 times as much electrical energy out of it, then you can then use that electrical energy to put back into the system and power it. And we've been able to do that now, and we've had a self-powering reactor running for 2 hours this year. Now, we've also had them producing 5-time electrical reactors producing 5 to 30 times power out. So we are able to self-power a reactor, and we're able to have additional energy for exporting, selling, or using. And then on the thermal side, which I'll come to, we're able to basically create up to, well, we've seen 80 times more energy out of a reactor, 30 times regularly on a specific variety sitting behind me. So you can take that energy, which can be in the form of high temperature air or steam, and you can put it through a 30% efficient engine or a better 50% efficient engine. So you can self-power the device and you can export the additional electricity and heat from such a device. Water, as it's been known for some time, but it's had there have been many experiments on this. Water can be millions of times more energetic than fuel oil. It's because basically nuclear reactions are far more efficient than chemical ones. What you've got to be able to do, though, is create an environment where you can create nuclear reactions. One is efficiently and safely. Now, if you look at conventional fission and fusion, you're seeing basically large amounts of radiation being produced during these processes. But in low energy nuclear reactions, they pretty much all use or create condensed plasmoids, which are like 10 to the 26 times of electrons together. So they are, well, they can be seen in nature. Like you could say lightning, the aurora, or ball lightning is condensed plasmoids, huge quantities of electrons stuck together. And in that sort of environment, you can create low energy nuclear reactions that don't produce hazardous radiation or radioactive materials. Now, key industry players in this area, well, you've got Clean Planet, as I mentioned already, in Japan. Clean Planet, they've partnered with a company called Miura. Miura is the largest manufacturer of industrial heating equipment in Japan. So it's not a small company, it's a big company. And In Europe, we basically, I guess, are probably the leading European outfit. And then in America, you've got Brilliant Light Power and Brilliant Energy. There are companies in America that are basically going down this similar pathways. Orion Energy at the top there has been going for probably a decade now, and they are based in Canada. They have some quite big reactors up there. Now, not everyone's producing excess energy. Some people like ARC and Orion, they're using the technology to produce they're using it for transmutation. So they're producing isotopes, medical isotopes. Orion has been focusing on taking radioactive materials and making them safe. So LENR, catalyzed fusion, as we call it, is actually also a fission and a fusion process. So in our reactors that I'll show later on here, we can also see that oxygen is, for some reason, coming down to carbon. And there have been many examples of that, which I'll go on to later. And other innovators in the field, the European Union's Clean HME program, Orion Energy Canada, High LENR is a new startup in India, Prometheus in Italy are just a few of the leaders in this space. And they're all exploring the low-energy nuclear reaction pathway potential for applications, ranging from heat production to distributed power generation, and as I mentioned, transmutation. Now, we're not standalone companies. There's been for many, many years, in reverse order, I'll mention the International Society for Condensed Matter and Nuclear Sciences. It's the key scientific institution. It's been going for over 30 years. Every 2 years, it organizes a scientific conference called the ICCF conferences. The next one is going to be in Japan in June, July, May. May. And so if you are very interested in this space, I would suggest you make your way to Japan, where there'll be approximately 160 scientists and scientific teams actually out there for a few days discussing the science behind LENR. Now, man actually used fire I think they controlled fire for approximately 1 million years before we understood in the last 100, 150 years how fire works, the oxygen from the air, basically mixing with the hydrocarbons and releasing chemical energy, releasing thermal energy from a chemical process. Now, catalyzed fusion, in a sense, LENR is very similar to that we've got working reactors out here. Our company has 5 different types of working LENR reactors. There are 2 main groups, the lattice-enabled reactors and the purely plasma reactors. There are many contentions how the devices work. As Professor Brian Josephson, who is a Nobel physicist at Cambridge, Trinity College, he said, when I asked him, could you write a specific summary of LENR pathways? He goes, look, it's going to be argued over by physicists probably for at least another 20 years. So why don't everyone just get on and make it work rather than arguing about who's right and who's wrong on the LENR pathways? And on that, LENRIA is the industrial association representing low energy nuclear reaction technology. They've been going for about a decade. They were formed by Professor David Nagel in the States and Steve Katinsky. And they've been promoting LENR for about a decade now into Congress and other organizations. And through their work and the work at MIT, they've managed to get the ARPA funding for research into LENR pathways. So thank you, Dave and Steve Katinsky, and many people over at the Condensed Matter and Nuclear Sciences International Society. They've been doing great work for 30 years, and please join in at the conferences and look at their website. Now, the main thing for any new energy source is going to be the cost of it. And this is from the Lazard's report last year, where we have superimposed in there the estimated costs, which are pretty reliable estimated costs of catalyzed fusion stroke LENR energy sources. So this is the levelized cost of energy. The basically takes into consideration the cost of producing energy, installing it, and selling the energy. You'll see there at the top, we have catalyzed fusion stroke LENR. Now that is 5 to 10 times cheaper than any other energy source that's currently on the planet that's stable. Now, wind and solar you see basically, but they all need batteries, or they all need oil and gas and to basically back them up to provide a stable, reliable energy source for our modern 24/7 economy. Catalyzed fusion, as we'll go on to do, has the ability to basically do this because it's a very low cost form of producing energy, which I'll explain why. So there's the comparison. Why are we focused on LENR? Simply because it's so much cheaper than anything else. And those costs basically come from the costs of the equipment behind us in the other laboratories. We're buying equipment every week. We know what the supply chains are like. We don't necessarily need to go to specialist manufacturers, capacity manufacturers, transformer manufacturers, PLC manufacturers behind me, water pumps, heat pumps, hydrogen pumps, etc. So it's not complicated equipment, nothing like you would see in a tokamak. It's more like a car engine technology. So what is a condensed plasmoid? It's the analogy I use is lightning or ball lightning or fork lightning. But these are created in a laboratory. So on the right there, you can see that we've got a little reactor with what looks like a little bit of lightning inside of it. And I'm going to try now and play the video of that we recorded earlier. Play video.
Oh,
Okay.
you know what? I should mention. So, it will not play videos with
Okay,
StreamYard.
fair enough.
Yeah. Now, if you have, so what you can do is if you wanna play the video, we can share a video screen if you want to do that. Or
I can.
or
It's literally I've got 1 minute of video, and I think it'd be very useful for everyone to see just one of the devices running.
Oh, okay. So why don't we do this? Do you think you could bring that open in a browser window, or?
Yep, on my yeah. You can share the screen with me. You mean basically yes. Hold
Yeah,
on a
okay. So
second.
yeah, if you drop the video, just drop that into a browser window. Sorry for interrupting your presentation, but
Not at all.
yeah. So what I'll do is I
I'm
will
in
take.
marketing. Yeah. It's I've uploaded it on your site, by the way. So
Okay, so then click the present button.
yeah, present button. Yes, got it.
Yeah,
Yep.
and then share screen.
Yep, got it.
And it should bring. I mean, it'll let you do the entire screen if you want to maximize it, or you could do a Chrome tab if the video is in a tab.
I see. Okay, that's where it is basically. Yes.
Yeah, StreamYard uses, it's interesting, this is an aside, it uses a ton of extensions that they built for Google Meet. And so,
Okay, yeah, I'm semi-familiar with it in that case.
yeah, we use it because it multi-streams. It goes out to several different channels at once.
Yep, got it. In that case, I will go to marketing and I will go aerosol.
Yeah, and no stress. We APEC is, we're
Yeah.
always loose. We have lots of interruptions and
Yeah,
general chaos. That's the nice thing about doing a science conference.
I'm gonna share my whole screen now. Okay, share my entire screen. So
okay, yeah, if you're comfortable with that, just be aware, right? It'll show your desktop. So
I'll get the naked ladies off it first. So here we go. There we go. So that's on my screen, entire screen, share my screen.
Okay, there we go.
And I'm going to bring up that video now. Can you see the video?
Yes.
Okay. Yeah. So it's a very short video. It's 5 seconds, but I'll play it once or twice. There we are. So I'll do it a couple of times. So this is a LENR reactor, and it's a plasma reactor. What we've got is we've got air basically going into the reactor, so there's no complicated fuels. We've got a little catalyst in there, but there's the fuel is actually the moisture from the air. So if you can imagine, we're a propulsion conference. So if you imagine a jet engine, it's going through the air, it's sucking, basically the turbofan is all just literally ramming air into itself, a jet engine. This is what would happen if you had the combustion chamber of a jet engine, or basically running an LENR, running this process. So So if you look at the back end of a jet nozzle, it's a couple of maybe 1,500 degrees centigrade out the back, because that's the design limitation of the turbine blades. The temperature coming out of the top of this little furnace reactor at the moment is, at the moment, it's probably 600 degrees centigrade. But if we increase that temperature by decreasing the amount of air going through it, or increasing the pulsing on the electronics, you would see the same temperatures coming out of a reactor like this than you would do a jet engine. So simply, I would say that in the next 18 months, our plan is to basically put that into a little turbofan on the front of it and demonstrate that you can produce a lot of thrust from air. So that's using air. Now, other devices that I'll show you, we can use water, or we can use hydrogen, for example, and we can get up to 80 times more energy coming out of the reactor than the electricity we're actually putting into it. So
and Haslen, let me know. I'm sorry. Let me know when you want me to put the slide deck back up.
Yeah, so that's basically, I've just shared there an LENR reactor that's very good for producing heat. Now, our contention is that when you use hydrogen and oxygen together, the oxygen is the primary producer of photons, as it basically converts down to carbon. And we also have some hydrogen reactions inside there. And it's very interesting that we're getting photons out of that. The next video I'm going to show you is going to be producing electricity, almost pure electricity out of the next reactor. So there we are. There's that one for the ionized space propulsion type stuff. So go back to here again. I'm going to go back to here. Go H2. Here we go. So this is a 1-minute presentation. I'm going to talk through it. So on the screen there, you could basically see a heat exchanger. There's a white energy cell in the middle. We call them energy cells, LENR reactors, catalyzed fusion reactors. And on the back, you can see a hydrogen pump. Now, the hydrogen is simply going around the circuit. So the hydrogen eventually would all convert to helium inside a system like that. And that's the heat exchanger. Sorry, we had a very artistic cameraman doing this. And we're going to go through the startup procedures now. So we're turning the power onto the system, the PLCs, basically turning on the hydrogen pump, basically turning the system live, putting the heat exchanger fan on. We're basically regulating the pressure of the hydrogen inside there. Basically, we lock it off. We flush it first and then lock it off. We now turn on the electricity, and there you are. Basically, we have a lovely arc inside there. Now, if it was a standard arc, it would be producing maybe light, but actually in this case, it can produce electricity. And this reactor is designed to produce 10 kilowatts of electricity going into it and 70 kilowatts of electricity coming out of it. So this could be a self-powering device producing lots of electricity for ionized space travel, for example. So Tim, that's those videos shared, so we can go back to the presentation. There we are. I'll stop sharing my screen. There we are. Thanks very much. So anyway, that was the reactor working on the right there. So depending on the fuel that we put in, whether it's a gas with lots of oxygen and hydrogen in it, i.e. air, or whether it's a purely hydrogen-rich environment, then it produces electricity. And our contention is the condensed plasmoid is key to this. There's many research papers, white papers produced on condensed plasmoids since the 1950s. And this particular phenomenon is responsible for the transmutation reactions happening. Now, there are different, I call it electron-induced or low energy nuclear reactions, where there are basically these condensed plasmoids. Hot fusion, they basically create huge amounts of heat, whereas we're using electrons to basically initiate the fusion reactions. And there are the main types. There are metal lattice ones. So these are where nickel, nickel or palladium nanopowders are infused with hydrogen. They're heated and they produce a lot of excess heat, and then that can be converted into electricity. And that's what Brilliant and Clean Planet have been doing, and others like High LENR in India. Then there are the vortex reactors, which is the one on the right that I showed a video of earlier. That one's running at nighttime on the right there. Then we have cavitation reactors, which are water-filled reactors. We have those running. That's the first one we started investing in ourselves. That's 10 kilowatts in, about 70 kilowatts of heat out. And that's steam, high temperature steam. That can then basically drive an engine, good old steam engine. And then that can create electricity, and you've got a combined heat and power plant. Now, we've also got electron tunneling. Electron tunneling energy cells are where you have a hydrogen over a specific surface, and the condensed plasmoids form on the surface. They almost feed off the hydrogen and release electricity in return. And those devices are self-powering at the moment in one of our labs. As I said, we have there's no harmful radiation coming off these devices if they're used sensibly, like a microwave. Microwave has a little shield around it, microwave oven. And we often have the Technical Electrical Institute of Portugal that is with us in the laboratory, plus our own detectors. So we check for alpha, beta, and gamma radiation coming off the machines. There is no change over background radiation. And we also measure a wide field of the electromagnetic spectrum for things like static electricity, for example, that like car engines are very sensitive to that, and radios. And so we are checking all the time, and even on the electromagnetic side, we are within less than 5% of what the European Union allows, so 95% safety factor on that. So it's a very safe technology. There's no ionizing radiation being produced if they're used sensibly. Now, in a propulsion application, which we'll go on to, we can ramp that power output out, i.e. the COP factor, the Q factor. So we'll come on to that in a minute. Genesis of what we've been doing. So ENG8, as I mentioned, is one of the companies in the space. We started off in 2017 investing in a technology that had been developed by a professor called Professor Vladimir Leonov and his team. And Professor Vladimir Leonov and his team were working with a plasma formation in water. It was quite interesting. So we came along. We could see that he could boil water. A kilogram of water or a liter of water could be boiled off for much more efficiently using plasma than it could be using electric heating element. So electric heating element boiling off water is a factor of 1. But if you can boil off using half that energy, then it'd be a Q factor or a COP factor of 2, for example. So he had about a factor of 1.3 when we came along and started investing. Then going forwards into 2018, we basically were getting higher Q factors coming out of the devices. We were pressurizing them, getting much smaller bubbles. Our contention there is that the bubbles are filled with plasma. That's where the condensed plasmoids are formed. That's where the LENR reactions happen between the oxygen and the hydrogen in water. And the evidence for that can be that 5 liters in a stainless steel vessel, 5 liters of water after 24 hours can become 4 liters of water and 1 liter of oil. So it's very interesting. Now, many geophysicists have speculated for many decades that the oil in the Earth's crust could never have come, the huge quantities of it could never have come from rotting plants or fossilization of plants, fossil fuels. Certainly couldn't have in their opinion. And we can show that under the pressures and temperatures and electromagnetic fields in the Earth's crust, we can see that water very efficiently becomes hydrocarbons. And you can see them literally long chain hydrocarbons forming in front of your eyes whilst you watch an LENR reactor running with water inside of it. So yes, the biggest source of renewable energy on the planet is the oil that's actually in the crust. I'm sure British Petroleum and the oil companies like to hear that one. Then going forwards, we were ramping up size. So people ask us, why have we got small LENR reactors in the kilowatts of 50, 70, 80, 100 kilowatt size? Well, we actually decided to go big at one stage. We had the Advanced Materials Research Centre in Sheffield in England basically machine us up the one in 2021 on the screen there. It's 0.5 meter to 1 meter tall. It can run up to 500 atmospheres, 600, 700 degrees centigrade. That unit there, basically, we met with the National Grid PLC in England. National Grid's head of technology said, why are you bothering with these big devices? They said, actually, the grid has pretty much got no more electrical capacity to be transported through the grid. So you should be focusing on small reactors that can be used in people's homes, that can be used in cars, they can be used in trucks, not 0.5 megawatt to 1 megawatt size ones. So we went, okay, we got that. So then we started focusing on smaller units that were much more lighter, cheaper to make, and more efficient. So as we go into 2023, we basically had at the laboratories we rented at the UK's Atomic Energy Authority facility at their fusion center. We had five times more electricity coming out, and now we've got standalone devices, self-powering, producing excess electricity. So these devices are ideal for all sorts of different forms of propulsion and powering different forms of propulsion tech, from jets to rockets to plasma thrusters. That's the one that I showed earlier, since I had a screen share. 10 kilowatts in, it's designed for 70 kilowatts out and 20 kilowatts of heat. Now, you can see how simple that device is there, plus the power supply unit, obviously a bit more complicated, but these are not very complicated devices. So once you get the power electronics side right. Energy outputs, I'll just summarize that. So we've got heat is the primary output for some types of reactors. So if we've got a lot of oxygen around, like in water or air, then superheated air for jet engines, basically you won't need hydrocarbons. So the fastest way of decarbonizing the international airline industry is to basically use LENR jets effectively. Electricity, we can produce electricity by either direct electricity from our machines. We produce very high voltage electricity. It's like 100,000 volts, high frequency and very high amplitude. That needs to be stepped down to be used and put back through the machine to self-power it, and then into 400 volts AC or whatever everyone needs, basically for their use. One thing I haven't mentioned so far, let's go back to that, is HHO. Used to be called, or is known sometimes as Brown's gas, ionized hydrogen oxygen from water. There are many companies now selling HHO generators, which are electrolysis devices for cars. Using HHO for when you're burning diesel or petrol in car engines or truck engines, rail engines, boat engines, makes it a much more efficient burning process. Now, if you can basically electrolyze water for less than 33 kilowatt hours per kilogram of hydrogen, because hydrogen contains 33 kilowatt hours of chemical energy inside it if burnt in oxygen. Now, we found from plasma reactors, specifically with LENR processes happening inside them, you can produce hydrogen for 5 to 10 kilowatt hours per kilogram. So that means you can have your internal combustion engine, your truck or your car, and you'll be able in the future to basically run that truck or car purely from HHO. So you electrolyze the water, you basically run it through an internal combustion engine, you basically condense the steam through the radiator condenser at the front of the car, truck, train, and then, or aircraft even, and then you can then basically re-electrolyze through an LENR reactor and basically put it through. So Stanley Myers had a water vehicle in the 1950s. There were problems with either replicating the pulse rates or replicating the cathodes or the catalyst he was using. So goodness knows why that couldn't be replicated, but basically it works well. And then thrust, Rocket engines using LNER reactors, using either H2 or HHO gas, for example, can produce at least a magnitude or more energy out than you can on chemical reactions. Now, it's not theory, that's been done. So we're looking to collaborate with anyone from SpaceX. Peace, we're into peace, basically, peaceful applications, no military applications as far as we can help it. So if anybody's got a peaceful space project, then we're in, basically. Let us know how we can help. Independent validation is a very important thing, especially for investor confidence. So we've basically been working with different institutes. Some are listed here. So the University of Aveiro, they have CET, which is the National Material Science Center for Portugal. I'm actually in Portugal at the moment in the laboratory next to the University of Aveiro in their science park. And CET is here, so we can basically take a cathode, an anode, or a gas sample over there and analyze it to show that basically you've had transmutation happening. University of Cambridge, Professor Brian Josephson, I mentioned earlier, from Trinity College, Nobel laureate. He has been very supportive of us and assisted us getting some transmutation type analysis done at the Material Science Center in Cambridge, where an electrode was analyzed that had no carbon on it to start with. After being in an LENR reactor, it's got a lot of carbon on it, very visible. And that carbon also contains traces of boron, which we believe is going through hydrogen, helium, boron into carbon. So there's that. And Technical Electrical Institute of Portugal have been brilliant for us. They've also been supporting other labs. So we had a major US lab in here and in our facility in England twice. And they basically were supported by the Technical Electrical Institute of Portugal. They not only look for, they do the calibration of all the equipment inside here. They bring in their equipment to run all the calibrated tests. So they've been absolutely great as well. And also Professor Jean-Paul Barbarian, who's a very well-known physicist in the LENR space. He was responsible for the calorimetry on the European Union's Clean HME program. So Jean-Paul Barbarian's now been in our labs on a couple of occasions, validating our reactions. And one basically recently, he said, look, your systems can self-power. I've seen them self-powering and they can be effectively self-power indefinitely. He wrote a couple of reports on that, or rather one report on that and one on the air cell system as well. So yes, so it's a very exciting time because we've had independent validations done. There are other LENR companies out there with some very, very good results. So it's not just us, there's many other organizations. Propulsion travel is a big thing for me. So on the right, there are some of the things I've been working on. That's me standing next to a 1/2 ton payload drone. And in a lab I had just before COVID. On the left, on the box, it's a Euro pallet sized box. So it's 1.2 meters long, about 4 foot for the Americans, 3 foot, 1 meter tall, 3 foot long, and wide, 2 foot wide rather. So it's basically shows the power density, and that's without really packaging these things. So that's representative of our next development, which is an energy cell in a space like that. That first unit arrives in the laboratory, this laboratory on Monday or Tuesday next week. We basically will be able to experiment with these modular units, and they can effectively go into the standalone power plants for our commercial customers, which are to do with industrial heating. But we've packaged those and put them in a patent application for aircraft. You'll see above. That's an aircraft there running water cells, interestingly enough, because we can take the water and basically create a lot of excess energy from it. It then basically goes through a steam expander, which is a steam engine, to basically power a propeller and then be recondensed and go back round. So, but the beauty of that is that you don't need to fill your aircraft up with fuel because you're carrying the water on board, and it's thousands of times more efficient than having fuel. You just keep running it around and around the system. And then also you don't have to worry about air. You can fly very high because you're not having to worry about burning air with your hydrocarbons. So there's some big advantages there. The image below it is interesting because that's using quantum propulsors. So another talk we can have on quantum propulsors. And the larger unit that I'm standing next to there, that's basically using a novel system for contra-rotating propellers that I was working on. So basically, you don't need to carry fuel, or you need to carry a very small amount of fuel because you can burn it or gain energy from it in a far more efficient way. And of course, if you're in space, then if you're on Mars, you're on the moon, or you're on asteroids, there's generally water around. So if you've used up all your, you've converted all your water on board to oil, then you can then basically go and get some more oil and go and get some more water and put it back in the system, or hydrogen, for example. So there we are. In terms of scaling these things, as I mentioned earlier, we did work a lot on the scaling. We've done the engineering work, as you can see there. That's a container, a 6-meter shipping container, 20 foot for Americans, basically 20-foot shipping container. 2.4 megawatts of energy can be produced in such a container without seriously packaging it all in. So the power density of these units is ideal for space, and it's also pretty handy back here on Earth as well. A 12-meter container would be about 5 megawatts of power out of one of those. Now we've been working on basically boats. I was presenting at the European Tugboat Owners Association conference, and they were very interested in class approvals. So we had meetings with DNV and ABS on class approvals for our system. So there's no hydrocarbons involved. There's no explosive elements involved going on board. So to do with IMO, so it would take probably 18 months to 36 months to go through class approvals for boats, commercial boats. And I'll go on to how we don't have to just put a standalone power system on board. We can do repowering as well. By the way, those people that are fascinated in LENR, there's a really good book there to read by a wonderful Hungarian called Joseph Papp. Now, believe it or not, as you may read the book first, that machine there looks rather like a modern supercavitating torpedo. That thing basically apparently crossed the Atlantic at 300 miles an hour underwater at least 70 years ago. So read the book, it's fascinating, and make up your own opinion whether he got across or not. Now, retrofitting. Retrofitting units is a far cheaper and more easy way of going about things. So creating a new jet engine, 10 years away with all the certifications for commercial use. Now, but if you could repower something, then you're not having to change the whole system. You're only having to recertify the specific components that you've had to use. So jets, as I mentioned, you could change out the combustion chamber, and it wouldn't take a huge amount of engineering to put a cathode and an anode in there and do something like that. But for ship engines, for example, because this was part of a presentation I was doing for the European Tugboat Owners Association, you could do HHO flame injection. So effectively, you're injecting just a different fuel into the engine system. You could do steam injection. Well, diesel engines came from steam engines. So effectively, you're injecting steam basically to expand, to pressurize into the into the cylinders, the pistons move down, you've got a steam engine rather than diesel engine, or you could make it purely pneumatic. So there's different ways you can convert a internal combustion engine into using an LENR reactor. New solutions could, of course, be direct drive. So it could be, as I mentioned, showed earlier, a steam expander, a steam engine driving a propeller. Power to weight ratios are fantastic for this sort of application because you don't have to, you're not carrying all the fuel around with you. Or you could do hybrid drive, so we can produce some electricity, as in the rig behind me, just behind my hand there. That device there produces electricity, so that could then be put into a super capacitor or battery, or a combination of super capacity and battery. And then you can then use that for your car, or you could use that for creating a plasma thruster if you're in space. So different ways of doing different things. We're super interested in finding companies that have a budget and are willing to collaborate with us. So we've been talking to a couple of members from the European Space Agency. We look forward to engaging more with the European Space, or more of those people at the European Space Agency. In America, obviously, SpaceX, we would love a conversation with SpaceX. If anybody's listening from SpaceX, it'd be a fantastic conversation to have. And any other space organizations out there, we're here, and we've got tech to demonstrate, bring a scientist to our lab. Questions, we know the questions, if there's any chat, basically, questions in chat, we can go through those in the next 9 minutes left. But also I have a slide here, which is people can check later, which is very useful because many people have been very skeptical about cold fusion, catalyzed fusion for many years. So they're the links. Even Sabine Hosenfelder has been waxing lyrical last week about cold fusion again, catalyzed fusion, LENR. There's the LENR org library, which is a fantastic library of nearly all information. Carl Page, Larry Page's brother, who runs the Anthropocene Fund, he's basically got paid, he invested in AI, creating an AI to organize it all. Excuse me. So that's very well organized. DARPA have been running a program to look at the DARPA updates. That's DARPA, no, ARPA rather, not DARPA, ARPA-E. Goodness knows what DARPA's been doing, that's secret. There's a new site for LENR, the CMNS group. It's on Telegram and it's on email, so it's very useful to go to for information. There's the Condensed Matter and Nuclear Sciences Conference. It was in the USA. It was then in Poland last year, and it's going to be in Japan this year. Solid state fusion formation of a scientific field, that's the ICCF 26 I mentioned. Cold Fusion Now, a very good journal. The LENR forums are very, very good. The Japanese are really worth looking at with their quantum energy at Clean Planet. And NASA, of course, have been looking at this for many years. So we'd love NASA to come over and spend some time with us too. So with no ado there, Tim, that's me. Me gone through in 52 minutes. So if there's any chat or any comments there, I'm all yours.
Wonderful. Haslen, thank you so much. So true to our tradition, I'm going to bring folks in, and let me see, we only have a few backstage. Let's give an enormous applause to Haslen Back. Sir, thank you so much. Yeah, and we do have a few minutes for questions. So actually, I had a question. Someone pinged me in chat and said they wanted to ask, how long was the longest continuous run of this device so far?
4 hours, and that's based on the fact that the guys need to go home.
Okay, okay.
So we've only run it for 4 hours. Now, behind me is a new automation system. So that'll give us the ability to run at night without the guy sitting there dialing away, keeping tune. Because at the moment, the devices are quite, they're manually operated for the tuning side. So, but with the new automation system, that will enable us to run them overnight. And also, we are implementing AI. So an AI box next to each unit. So by the end of the year, we will be able to have an AI system, like a little supervisor for each unit. So by the end of the year, rather than having one manual rig, we will have in each laboratory, we'll have 5 rigs. So they're running at least one is running continuously with an AI supervisor. So we learn a lot more. Our rate of knowledge is going to be probably 1,000 times faster by the end of this year than it is now.
That's amazing. That's amazing. And again, so the video that you showed us, and people like in replay, they can go back and look at that. The video that you showed us, I guess I have a couple of questions. The first one is, those are probably on the website, and I'll put the website up in a moment. And then the second one was, it looks like, again, you mentioned it was using water vapor from the air. So
yes,
if you were going to run this like for space applications, then you would need to you'd need to carry a little bit of water and carry basically just kind of your air tank. But
what we actually do is we would run it closed circuit. So you would just put a little bit of more, you would have a like run it nitrogen, and you would just a nitrogen circuit like we have here, the nitrogen black tank, and then you put a few drops of water in the circuit, and off she goes, and there you are. There's your fuel source.
And the weight sounds like it would be a lot lower than it would be for like a traditional LENR cell, right?
Yes, the traditional LENR cells are powders, basically metal powders, and then imagine a rocket. Basically, it's just basically a container with fuel inside it, and it's burning at a COP1. It's a chemical reaction. Whereas now we're able to run these things at 30 to 80 times more energy out than the chemical reaction. So you would be able to have a lot less fuel on those rockets.
Yeah. And so I just put the website up. And I'm going to drop a link into chat. The website is eng8.energy. And I just posted that into chat in the comments. But so folks aren't going to necessarily be able to see that. And I'll just scroll through it very quickly. And again, Haslen, thank you so much for presenting on this. This is, it's
pleasure.
LENR is one of those things. I don't think it gets the attention that it used to, and it definitely needs it because there is a ton of work going on in this area. So,
yeah, it's great because I think this year is going to be a really big year for LENR because people have said, oh, you can't reproduce in a lab. Well, just go and look at the commercial companies out there with working LENR reactors that are working on commercialization at the moment. It's like, they're all around the planet. So yeah, it's definitely coming out, as they might say.
Okay, and yeah, and again, I'm just scrolling through this very quickly. It's eng8.energy, and so it's not a .com domain; it's a .energy domain, and people can learn more about this there. And then, do you have links to the videos? Do you have like a YouTube channel? Or
on the website, there is links basically to videos, and if people put ENG8 into YouTube, I'm sure there's a few videos up there.
In fact, I see it right here. Okay, and so
I'm more of a techie, so I don't normally go and look at the YouTube videos.
Yep. So you know what? Let me do that. We have a couple of minutes. And do you guys have any questions? Drew, David, Mike, do you guys have any questions for Haslen? Okay, here is the YouTube channel. And
yeah, there's quite a lot of those videos on YouTube. Yeah.
Yeah. And so I'm going to scroll up so that folks can see. Oops. Okay.
You'll also see that there's a lot of how should I say, a lot of trolls basically out there. A lot of people stuck in the old hot fusion sort of like physics. So without even considering reading, being informed about LENR, they just simply say it's impossible. And it's like, oh my guys.
And this is a little bit off topic, but I have a friend. He writes essentially a Dear Abby column on Medium and on Quora, and everything he does is positive and uplifting, and it's just day-to-day stuff, right? And he gets he has a massive readership. I mean, hundreds of thousands of people. And he gets tons of troll comments. And I asked him, I said, why are you getting these comments? And what do you do about it? You know? And he said, you know what? No matter what you do, no matter how innocuous, you're going to get troll comments. He's like, just don't take it personally. He's like, I don't even respond. I just ignore them. So.
Exactly, yes. Just ignore Substack. Just ignore some of the Reddits and things like that, yes.
Yeah. It's people taking out their daily frustrations on other stuff. They just find something that, you know, so.
Yeah, very true. Drew, did you have a question, Drew?
Yeah, this seems more like a battery than a rocket engine. So
no, not at all. A battery stores energy, whereas this basic,
it's a little dynamo.
Yeah.
I'm saying it's an energy device, not really a propulsion device. So you said it's like 80 times more efficient than a rocket than a chemical reaction.
So if you stuck, let's say for example, you stuck hydrogen and oxygen through a rocket nozzle, you'd have a unit of 1 thrust out of it. But if you stuck that through the LENR reactor, you'd have 80 times more thrust out of it for the same.
You get 80 times more hot out of it. Thrust is a function of heating up the mass. So unless you have 80 times the mass,
yes,
you're going to have to have an enormous amount more hot.
Yes,
so
okay.
I understand that this is really revolutionary. I get all that, but it seems like it's better suited toward keeping the lights and the water running in the spaceship than it is trying to you don't have any real way to heat up mass. You don't have any mass to heat up. You've got a lot of energy, but unless you've got a lot of energy and a little bit of mass, you're not making a propulsion device.
Unless you use the hydrogen oxygen basically, which is in the water, and then you basically put that through your rocket system. But I'm not a rocket scientist.
You'd have to have a lot of mass.
Yeah,
I just want to.
It's fascinating. I didn't realize that. Thank you.
Well, and guys, we are at the top of the hour. So again,
thank you, Tim, for so much having me on.
Oh, and Haslen, thank you, guys. Let's put our hands together one more time for Mr. Haslen Back. And I have put links in. So what I'm going to do is take everybody out now, and Mr. Dr. Mike McCulloch. Mike, welcome back, sir. You have presented several times at APEC. I'm overjoyed to have you back. And so I am going to add your slide deck. And I think this is the one to start with, right?
Me okay? Can you hear me?
Yeah, I can now. Wonderful.
Yes, okay.
So let me mute myself out, and I would say take it away, sir.
Okay, well, hello. So I'll be talking about thrust from quantized inertia today, and I thought I'd start with a picture by Claude Monet. And this is a picture that represents what really started me down this pathway. Two ships at sea here with waves around them, and there would be fewer waves between the ships than outside them, and that would tend to move them around, to push them together maybe. And that made me think, what about the quantum vacuum? That's another kind of wave. What effects does that have? And the result of this was quantized inertia, which I'm going to argue is a major shift for physics. I'm going to show you some astronomical evidence for it, some of it, and then go into the laboratory evidence for QI thrust, and then talk about possibilities for interstellar travel. Okay, so just a background, my background, BSc in physics, PhD in ocean physics. I was a scientist at the UK Met Office modeling waves for a while. Then I was a lecturer at Plymouth University in the UK, and then I was funded by DARPA to work on this. And I published 26 papers and 4 books so far, proposing this theory of quantized inertia. Okay, so inertia has always been a bit of a mystery. So many years ago, Aristotle believed that the default state of mechanics was to stop. But of course, with the benefit of hindsight, we now know that that's not a good model, because stop relative to what? Velocities are always relative to something else after Einstein. So Philoponus, who was a Byzantine Greek in about 500 AD, and later Galileo, who read his books 1,000 years later, said that the default state of matter is a constant speed instead, which gave us the idea of inertial mass, that things keep going in a constant speed unless you stop them. So this was great because it allowed Galileo to see that the Earth did not have to be at the center of the universe, still at the center of the universe. It could be moving, and that would still work in physics because everything on the Earth would move around with the Earth with inertial mass. But what I'm trying to say with QI is that the default state is not a constant speed. It's actually a minimum acceleration, which is rather different, and it attacks some of the fundamentals of modern physics. So I fully accept the pushback that I've been given. Will this shift take 1,000 years to be accepted? Well, I don't think so, because this time we have social media, so information can get out, and also get out very fast globally, and also because this particular paradigm shift has a lot of uses that I'll try and describe. Okay, so the model I'm suggesting is as follows. If you have the model for inertia is as follows. If you have an object, this black circle here, which is accelerating to the right in this picture, then it's well known now that it will see what's called Unruh radiation. Actually, Fulling-Davis Unruh radiation. That's predicted by quantum mechanics. It's a thermal bath of heat that the object will be surrounded by. So I've tried to show this with the red mottling here, and this will be a collection of virtual particles and waves that I've tried to indicate here. So this Unruh radiation has now actually been seen by Lynch et al., and I'll talk about that in a minute. But the other thing the object will see is a horizon on the other side, the side that it's accelerating away from. And this is predicted by relativity. It's a consequence of the fact that information from this black area will never catch up to this object that's accelerating. So the new part of quantized inertia is simply this, that I'm assuming that this horizon damps the Unruh radiation. So I've tried to indicate that by showing this area is blue and it's colder. It's got less Unruh radiation, less thermal radiation in it. And this damping is very much like the Casimir effect. So in the Casimir effect, if you have two objects, for example, here I'm assuming the horizon and the object are the two plates of the Casimir plates, then some waves will be able to exist between the objects like this one, but some will not fit. And so we get a kind of cold region here. This means that these virtual particles or this Unruh radiation will be pushing the object from in front, but not behind. So it will tend to push it back against its acceleration. Whatever acceleration it has, this Unruh radiation, the imbalance in it, will oppose that acceleration. The other way to think about it is that this provides a temperature gradient from which work can be extracted, which is what we know as inertial mass. And there's another way to think about it as well, using information, but they're all essentially the same thing. So I published two papers about this, conceptual papers in 2007 and 2013, and this is the model. But it has one great advantage in that it doesn't just predict the inertial mass that we know, it's slightly modified. Oh, this is just to show that Unruh radiation was confirmed in 2021 by Lynch et al. They looked at data from CERN, looking at positrons hitting silicon crystals, a bit like this, and they saw light being emitted, and they showed that the spectrum of the light, shown here, was just what was expected from Unruh radiation. You can see this x-axis is the frequency of the light. This is the intensity here. The data is the black dots, and the expected Unruh radiation spectrum is a blue line here. So it's pretty close. And the paper they published is here in Physics Review D. Okay, so this model does differ from the old inertial mass as follows. So if you've got an object which is accelerating at a very low acceleration, incredibly slow, about 2 × 10⁻⁻10, then this horizon, this Rindler horizon, moves further and further back until eventually it goes behind the cosmic horizon, which is the boundary to what we can see anyway, which is about 10 to the 26 meters away. And when that happens, the asymmetry that was present before disappears. So now we just have the same amount of under radiation all around, no asymmetry and no inertia. So this model predicts that for very low accelerations, inertia will tend to disappear. And this can be summarized in this formula here. So we've got the modified inertial mass is equal to the original one times this factor, which depends on acceleration. And you can see that when acceleration becomes very small, this term blows up and inertial mass decreases. So what does this mean? Well, it means, for start, that we can solve the galaxy rotation problem very simply. So here's the Andromeda galaxy, it's spinning around. The stars in the center are spinning fast, orbiting fast. The ones at the edge are accelerating very slowly. The problem is that these stars are moving faster than they should be. So they should, given the centrifugal force, spin off into space, but so they invent dark matter, add it to the galaxy to try and make it all balance out. But what quantized inertia predicts is that the inertial mass of these edge stars, low acceleration stars, is reduced. So the centrifugal force is reduced, and it turns out it's reduced by exactly the amount needed to balance the gravity of the visible matter of the galaxy. So this solves the galaxy rotation problem, and I published 2 papers on that. So it works perfectly. There's no adjustment needed. It's very simple. You just need the visible mass of the galaxy, the speed of light, and the Hubble scale. So that's very useful astrophysically. And also to prove it beyond any doubt, you can look at any galaxy. There are thousands of them to choose from. And in a sensor, they behave perfectly well with Newtonian physics. But here, the accelerations are high, so the underwaves are short. Further out, at higher radii, the accelerations are lower, so the underwaves are longer. And at exactly the radius in the galaxy at which the underwaves become the Hubble scale, that's when the problems begin. That's the exact point the problems begin. So this is direct evidence that it is quantized inertia that's causing this this anomaly. Okay, so I think it's clear we now understand inertia. So can we control it? Understanding usually is followed by control. So yes, I think we can. So normally, in order to launch something into space, we use rockets. So you collect chemicals, put them in the rocket, very heavy. You force them to ignite. The explosion directs hot gases downwards, and a recoil pushes the rocket into space. But with quantized inertia, there's another way to do this. So what you need is a very highly accelerated core. So I've shown it here. I've shown it spinning, but it could be accelerated electrons or microwaves in a cavity or something like that. And if the acceleration is large enough, then the underwaves will shorten to an extreme degree. So if the acceleration is about 10 to the power 20 meters per second, the underwaves will be a few meters long, whereas normally they're about light years long. If they're a few meters long, then they might start to interact with metal placed in the vicinity. So we can put a damper above this core here. This will damp the underwaves above, so the underwaves below will push the object up. And this means we've now got a propellantless method of thrusting. We don't need to carry heavy fuel, we just need energy in the system, and the underwaves will do the rest. So there may be several pathways to achieve this, and I think several of these practically have been available for some of them for decades. So for example, T.T. Brown in the 1950s or earlier looked at vacuum tubes and capacitors and sparks across them and found anomalous motion in them. Well, what I think is happening here is that between 2 metal plates like this, the underwaves are damped. So we have a lot of underwaves. It's hot outside, so I've shown that with red. Between the plates, there are fewer underwaves. So the electrons crossing over the gap lose inertial mass, just like the stars at the edge of galaxies do. And that means that there's in order to conserve momentum, the whole thing has to move to the in this direction towards the anode. And the mathematics works out as well. Quantized inertia predicts the thrusts that have been seen. Another way would be to use the spinning disk of Pokletnov, for example, which was a very controversial experiment done in about 1994. He had an asymmetric disk with a very fine crystal structure above and a coarse crystal structure below. And what that will do to under radiation is it means it will damp more under radiation above than below. So you'll have a gradient from hot to cold, and the disk should move upwards because of that. Then there was Roger Scheuer in 2001. He showed or claimed that the M drive moved towards its narrow end. So microwaves inside a copper cone cause it to move very slightly towards its narrow end. So this also works with quantized inertia, which predicts it. At the narrow end, more unruh waves can exist, but at the narrow end, fewer can. More waves are deselected by the walls of the cavity. So again, we have a gradient from hot to cold, and the object moves down the gradient, and quantized inertia predicts this quite well. Then James Woodward in the 1990s, he worked with asymmetric vibrating capacitors and found that they moved towards the thicker capacitor plate. He had a thin plate on the right-hand side, a thick plate on the left, and a dielectric and piezoelectric, in between. And again, the thick plate will damp unruh waves more than the thin one will. So you'll have this gradient down which the object will move. And quantized inertia predicts, well, the one experiment I can get a lot of information from, it predicts of this, of a Woodward capacitor. So yes, I'll just show that for the M drive, the quantized inertia predicts them very well. So this graph shows the thrust predicted by quantized inertia. The old name for it is MISC, and then the observed thrust on the y-axis. And if the theory works, all the data should lie along the line, and it does. Especially after correcting the M drive data, it turns out that if you put dielectrics in the M drive, it does make a difference. So when you take account of that, the theory works even better. So you go from these open squares to the black squares. So I published that in this paper in 2017. So at this point, DARPA contacted me and I applied for funding. I was awarded $1.3 million to try and demonstrate scalable thrust from QI in the lab. And so far we've had, well, arguably 7 labs have seen thrust that looks like QI. So I'll try and describe those. So the first success came from Frank Becker and Anke Batt, who read my papers and tried a capacitor setup. So a capacitor is a very efficient way to have a highly accelerated core. So you have a cathode and an anode made of aluminium foil or metal, some kind of metal. You have a dielectric. In Becker and Batt's case, it was Kapton and a plastic. And they charged this up to about 5 kilovolts with a small leakage code across it of microamps, a few microamps, and placed it on a digital scale and seemed to record a weight change. So what I think is happening here is that normally, if you have, say, an electron which is accelerated in quantized inertia, you get a lot of unruh waves in front, few of them behind, because you have this horizon damping them. So you get a pushback, which predicts normal inertial mass. But in the case of a capacitor, the electron is going across the gap. Very few unruh waves can exist between the plates because they're damped. So this gradient here, this thermal gradient which produces inertial mass, is no longer present. So the inertial mass of the electrons disappears, and in order to conserve momentum, the whole system, the capacitor itself, has to move in that direction towards the anode. So, in order to derive this, applying QI to a capacitor, we can start from the Casimir effect. So in the Casimir effect, the force is given by, well, this formula here, where A is the area of the capacitor plates, and D is the separation, and H bar and C are the well-known quantum mechanical parameters. So what I did here, in order to work out what was happening with QI, is replace this H bar, which has the units of joule seconds, with the energy that we put in to the electrons, which turns into the onward radiation, multiplied by the time that that energy stays within the cavity. So H bar goes to E times tau, and then you can write E as P times tau, and then if you work everything out, you get this for the force. So the force due to quantized inertia on the capacitor is the power input times the Q factor, which for an electron just passing across is 1, divided by the speed of light times the ratio between the speed of light squared and the velocity of the electron squared, times the area of the capacitor divided by the separation of the plates. And if you put in some of these values, you get this, this formula here. So the force is proportional to the leakage current times the area divided by the separation squared, separation of the plates squared. Okay, so does it work? It works very well. So this is the data from Becker and Batt. They published a paper on the archive in 2018 showing the force that they got from capacitors of different separations, where the plates had different separation between them, from very widely separated ones, 120 micron, down to about 10 micron. And you can see that the black diamonds show that the thrust increases exponentially as the plate separation decreases, up to about 6 millinewton here. And quantized inertia predicts this data very well within the error bars perfectly well. And I should point out that there's nothing in quantized inertia that can be tuned or varied. In a sense, this formula might be misleading, but this number here contains things like the charge on the electron, the mass of the electron, and the speed of light. The actual formula looks like this, and there's nothing in here that's arbitrary at all. So you can't tune it, but it works. Okay, so this the data from Becker and Batt was confirmed and improved on by Richard Mansell from an American company, Ivo, in Virginia. So they decided that a digital scale wasn't the best way to do things, so they used a pendulum instead to get rid of any electrostatic artifacts. And they tested in a hard good vacuum that's in Fredericksburg, and they confirmed Becker and Batt's results. They innovated a bit. They used a new dielectric, which I can't tell you about, but it hugely increased the reliability. The Kapton plastic tended to burn out very quickly. And they also stacked their capacitors, which improved the results as well. And just to show an example of the observed minus predicted, we have the voltage along the x-axis and the thrust here. The observations show that as you increase the voltage between the plates, the thrust increases, and the theory predicts the same thing. Okay, so Ivo themselves looked at artifacts, but I did my own independent study and ruled them out. So electrostatic effects with the environment can be ruled out because they had a control with a 60 micron separation. So they had a capacitor with a very wide separation, and then one with a very narrow separation. And the wide separation had a very, very small thrust, even though it still was charged up. So that rules out that. Iron wind was ruled out by vacuum testing. Interaction with Earth's magnetic field is far too small, and thermal expansion is also too small. So there's no effect that would cause this that we could see, except for quantized inertia. Okay, so then we set up a lab in Plymouth, so very similar to the Becker and Batt setup. We had the capacitor here, we had a digital balance, we had the charge put in via liquid metal gallons down, and yeah, we got some results. This is my chief engineer, Richard Arundel, and part of the setup. We slowly improved our system, making it cleaner and cleaner, and we got some good data in the end. You can see there's a few YouTube videos here showing our results. and some of them are shown here. So this is quite interesting because it shows that, in our case at least, we needed to heat the capacitors to get them to thrust. And this could be because we had Becker and Batt and Ivo had no difficulty getting a leakage current passing across their capacitor. We had far more difficulty, and we had a much smaller thrust as a result. And I think the reason for that is that Becker and Batt carefully sanded their capacitors. They knew well how to get the electrons to jump between the plates, and we were not quite so good at that. Anyway, it shows that the predicted thrust and the observed one agrees very well if we heated the plates. Heating is interesting because it reduces the work function of the metal and enhances what's called the Fowler-Nordheim tunneling, the electron tunneling across the gap. So that seemed to make sense. Then Ivo tested their system in space. So they used a 3U CubeSat of Rogue Space Systems launched by SpaceX, looked a bit like this, solar panels. And they had 2 QI quantum drives on board. So one had a thrust of 0.25 millinewtons, or a predicted thrust of that, and one 0.65 millinewtons. But unfortunately, before they could do the test, the satellite was lost. But they're trying again, so the next launch is expected to be, as far as I can tell, the 1st of March 2025. So you could watch out for that. And more recently, there's been a new independent validation. So Dr. Charles Buehler, who's a NASA scientist, ex-lead of their electrostatics lab, tried experiments. Well, he tried various different kinds of experiments, but some that were similar to Becker and Batt's configuration with the capacitors here. But the one that I looked at in particular, because they presented in their video enough information for me to quantify it, looked a bit like this. They had a plate with a dielectric deposited on it. So they didn't have 2 plates, they just had one. So that there was asymmetry there. And in a paper I published in 2018, you can use this equation here, involving the velocity, the potential difference, and the separation of the plates and their area to predict the thrust. And the prediction is 5.8 millinewtons, and the observed thrust was 4.5. But quantized inertia has something interesting to say about Buehler's method, in that it might be more scalable. So Becker and Batt's configuration relies on electrons passing across the gap only once. But Buehler's configuration seems to involve the electrons vibrating within the dielectric itself, which seems to me is a more repeatable way to do it. So this is yeah, quite interesting. And I'd like to get more data from Charles Buehler, if he would be good enough to send me it. So combining all these various lab tests I've discussed, the capacitor ones, there was another one done back in 2008 by Honda, actually, which was very similar to these. And as you can see, QI predictions are pretty good for all of these. For the Honda test, it was 14. They saw 14.5 plus or minus 4, plus or minus 4. Becker and Batt agreed very well. Ivo, our test in Plymouth, agreed very well, although, as I said, our thrust was much smaller. We didn't have as much experience in tailoring capacitors, I think. I think that's true. And then there was another test done in Italy, which was done by a company that don't want to be named, but it was a beautiful set of tests. And they also showed very clearly the effect of heat on their results, encouraging electrons to jump across the gap. That also agrees with quantized inertia. Buehler's test does as well, and there's very recently been another test by Barnhart and Ryan Weed of University of Southern California and Positron Dynamics, who the QI thrust was predicted to be 8.5, but they saw about 3.5, which is interesting because their setup was different to all these other ones in that they had a plate separation. The plate separation is normally about 10 micron or 20 micron. They had a plate separation of about 90 micron. So it could be that I need to look at the difference there. There might be a difference because they have a larger separation. And also, it's a shame that they're after they've just published a paper on this, they're dismantling their lab, apparently, which is, I see as a shame, because they had a very nice levitated setup in a vacuum chamber. Anyway, so thrust consistent with QI has been seen by 7 labs now, plus many others that I've looked at. For example, there was a test by NASA back in 2003 using a sparking capacitor, and T.T. Brown much earlier, as I've described. And also you can predict, it's very interesting that you can predict the behavior of so-called lifters, these electrostatic lifters that are quite easy to make using quantized inertia. And it could be that this also predicts them. I should say that the current theory for lifters is that it's an ion wind, but some of the data that has been collected, Eilat and Calderon, 2014, for example, they've shown that the thrust decreases if you have more wires above the lifter, which would not happen if it was ion drift, but would happen if it was quantized inertia and only waves being damped above it by the wires. Okay, anyway, so this obviously has many applications. The first obvious one is to replace ion drives and satellites. So taking the Dawn probe, for example, that went to Ceres in the asteroid belt, its ion drive shooting ions out from gases like xenon produced about 90 millinewtons, which is much larger than a Horizon drive would produce at the moment. But the trouble was that it had to carry its fuel, almost half a ton of it, and it needed 2 kilowatts of power. But all the same, it managed to get up to 27 meters per second in 1 or 2 days. But if we used quantized inertia, so we had a satellite called Horizon 1 maybe, and we used only the capacitors that we've seen, that we've used in Plymouth, so only 0.25 millinewtons, that seems to be a much lower force, but the weight is much lower. It's only 3 kilograms for the CubeSat. And it would only need 1 watt, which you can get from the solar panels on the CubeSat. So you'd be able to get up to 27 meters per second in 4 days, which is comparable. And with the higher thrusts being measured by Becker and Batt and Ivo and other groups, this would be certainly a way to replace ion drives with something much better without the need for fuel. Okay, so an application 2, so this is obviously more speculative, but for the first time, this kind of propulsion would allow interstellar travel. So I've worked with Dr. Kelvin Long in designing an interstellar probe that would use this kind of thing. So it would look a bit like this. You'd have a shield at the front, protect from interstellar dust, many capacitors, so 5,000. You can tailor it whichever way you want. They will be powered by RTGs. So there's one from the 1960s actually called Snap 2B that has enough power in it, and is only about 2.5 kilograms in weight, and it would have a high gain antenna to radio back information to the Earth. With something like this, which is about 50 kilograms in weight, you would be able to get to the Oort cloud using QI capacitor thrusters in about a year, and to Proxima Centauri in 10 or 20 years, that sort of thing, that sort of time scale. So you'd start off from our solar system, you pass through the Oort cloud in a year. Acceleration would be about 0.75 meters per second. You'd reach half the speed of light after about 4.7 years. You'd coast at half the speed of light for 4 years, and then you'd reverse polarity on the capacitors to decelerate, and you'd end up at Proxima about 13.5 years later. Obviously, changing the spacecraft slightly, you could change this, and improving the thrust, as I think we most certainly can, you could do much better. The best way to improve thrust and capacitors, according to the theory, of course, would be to narrow the separation between the plates. But in order to do that, you would also have to improve the dielectric between them. So at the moment, I'm searching for a much better material to use as a dielectric. Okay, so there are many applications apart from these. So obviously satellite station keeping, lighter satellites to launch. If we can boost the thrust, you can start thinking about things like flying cars and all electric aircraft. And I think it's also possible, it will be possible in the future to build structures that hover. If you are able to design a nanomaterial in the correct way, I think you could arrange it so that it damps Unruh waves more in one part of it than another. And that would create this Unruh radiation gradient, which would push on that structure. So it would self-thrust. So eventually, I think this will be used to launch things, much safer way than using rockets. Also, the great thing about some ways of propulsion using QI would be that in creating equally, so the spacecraft shell and also the people within it. So when you accelerate very rapidly, there'll be no whiplash. So this is much better than the present system. QI offers certain ways to get energy from the vacuum as well that I'm not talking about today, because well, this is about propulsion, but it does predict cold fusion as well. So so I was very interested to hear Haslen Back's talk about that, and I wonder whether he's considered a quantized inertia explanation for his catalyzed fusion. Interplanetary trips with QI become easier and cheaper, and as I said, interstellar trips become possible in a human lifetime. As well as these practical applications, QI solves so many problems in astrophysics and general physics. So many problems, in fact, that I've just written a book about them. And this is kind of a list of them. So it solves things like the cosmic flatness problem, galaxy rotation problem, as I've discussed, the orbit of our nearest neighbor in space, Proxima Centauri, which is also very strange. That's explained by QI. Flyby anomalies, things like these capacitor thrusters as well. So it has a wide range of application. So my next plan is to somehow set up a Horizon Institute, for which finances will be needed. So that the kind of plan for this is this year, or whichever year we start, to set up a lab. Maybe our first task will be supporting the IVO space test in March, or whenever it launches. And then to work in a lab to enhance the QI thrust by reducing the separation between the plates and improving the dielectric, modeling the energy extraction methods that QI suggests, energy from the quantum vacuum, and build that energy source, demo it, and then start working on an interstellar probe. I think the interstellar probe will be a perfect, I don't know, finale, you might say, to this, because it would require both QI ways to generate energy, perhaps, which would make it much lighter, and also QI thrust. It would all be wrapped up in this package, which would, I think, unite people and excite them. And we could launch by 2035 to Proxima and get some data from Proxima by halfway through the century. Okay, so to conclude, so quantized inertia is the first, that you might say, mechanistic explanation for inertial mass. It's a huge shift in physics on a par with the Philoponus-Galileo one, where they suggested inertia for the first time. This modifies inertia quite radically, and I realize that I'm attempting something quite difficult here, and there has been quite a lot of pushback. But I have a lot of proof now. I've collected it over 20 years, published 26 papers and 4 books on it. So galaxy rotation, wide binaries, Proxima Centauri's orbit, all these things are unequivocally point to quantized inertia as being the reason. There's no other theory that can predict them. Certainly not as simply. Many labs have also recently seen the QI thrust that was predicted. And as I said, I'm hoping to set up a Horizon Institute to work on this, both the theory and the applications of it, and also later to work on interstellar missions and interplanetary ones as well. So I've written 4 books on the theory. So the first textbook I wrote was Physics from the Edge back in 2014. This one here. I've written a more recent textbook, which is just out last year, called Quantized Accelerations. And I've also written 2 science fiction novelettes, you might call them, short novels, to try and explain the theory in a more accessible manner. And so Folding Up and Hacking the Cosmos there. So if you want to contact me, these are my email addresses, and please subscribe to my Patreon, which is here, One Step to Tau CET. And thank you very much for listening.
Mike, thank you. Let me bring everybody back in here. So let me take the presentation down, and let's put our hands together and give an enormous applause for Dr. Mike McCulloch. And Mike, were you able to give, you had your website info in there, right? I wasn't sure if I caught that.
Yes, my Patreon site. I put that up.
Okay. Awesome. And let me see. Yeah, and if you want to shoot that link out, I can put that up as well. But so let me see. Does anybody have any questions? Let me see. Tarl Cabot was asking if QI theory is related to the torsion theory of the universe.
I'm not sure what that is.
Yeah, I think it's
maybe
probably
you should
not.
know.
Let me ask Michael, did you have any questions? Michael just popped in. Okay, or Drew, or David.
Yeah. Mike, where did you get the information that you listed up there as Charlie Bueller?
He published
In one of your
one
slides.
YouTube video. Yeah, he's only produced one video as far as I know. And
All right, so you just extracted it out of the video?
that's right. That's all I could do. I have tried to contact him, and he hasn't responded.
Yeah.
Well, he hasn't responded directly. He's followed me on LinkedIn, I think.
Why don't you direct your questions to me, because I'm Exodus. Charlie and I are we're Team Exodus.
Yeah, well, and it's worth pointing out, Charlie has something going up. He has something that's going to the moon right now, actually. So if I remember right, doesn't he? Isn't his electrostatic experiment actually going up right now for testing?
It's launched a couple of days ago.
Yeah, so he's super swamped.
Let's see. I've just caught up to the current moment in the.
Yeah, he's been working crazy hours because they're going to land in, I don't know, 20 or 30 days or something. And then he does his little electrostatic.
Sorry.
Magic.
Unmute.
Let me see. Okay.
But, one thing I wanted to mention is I'm pretty sure I know what data set you're drawing your conclusions from our data. I don't know about any of the other stuff, but the test that you're talking about, that was a long duration test. So that was all bound charge. So what you're seeing is thrust that's from a thruster. That's the thruster that's completely disconnected from the power supply. That's just hanging out, waiting to discharge. So I don't know where all this leakage current is or whatever that you're talking about, but it isn't happening in our system.
Okay.
Yeah, I can send you the paper that I referred to from 2018 on that. If I get your email, I can send that to you.
Yeah, I mean, if I understand Drew's system correctly, this is something having to do with the electron clouds around the atoms in their system, which, I mean, that might explain why, allegedly, according to Thomas Townsend Brown, who did similar experimentation, that could explain why bismuth and tantalum and things that have relativistic, like behaving electrons might have more of an effect
Yeah, and then Michael, did you have questions? Sorry, it looked like I think you were following it online, so there was a time delay. Did you have questions for Mike?
I did. I guess it hasn't been tested yet in space then, according to the talk I just
No,
ran through. Darn.
not yet.
Next test is March. I guess what went wrong, and what can be done to correct for that in the future test, I guess. Or if you can talk about that.
Yeah, I don't know all the details because they don't really, they haven't really said. So they simply lost connection with the satellite at some point.
Darn.
So,
That communications with satellites is no easy task, as Drew from over at NASA, you probably know. Well, you guys probably both know.
Yeah, the area that we're in, right? The technology and the science keeps getting more complex, and the more complicated things get, the more difficult it is to control all these variables. I was doing some work last week, and the amount of complexity involved with it was just insane. It was unrelated to this, but for me, it was a reminder, and the same thing would apply to what Drew was working with, or what any of us are working with, is the level of complexity, right? It's systems that are composed of systems. And like in terms of the satellite test, right, you've got all of these space systems mixed up with the propulsion test itself. And my understanding was the space systems were the ones that had the issue. So, but it happens, right? I mean, look at SpaceX. They, how many rockets have they blown up so far? So,
test in orbit would still be the best thing to do. Interesting that the temperature gradient was relevant to the effect. I think Todd Desiato had a similar idea. Maybe you guys should get in touch. I think his is based on a polarizable vacuum sort of model, though, instead. But
Todd Desiato, okay.
Yeah, I don't know. Yeah, he also mentioned this. So, what else was I gonna ask about? With heating, is it possible that there were some thermal effects as well that were not unaccounted for in the other experiments?
We tried to test for that. We reversed the capacitors quite frequently to check it wasn't some buoyant effect. So no, I don't think it was buoyancy or a thermal effect. But I am trying to publish a paper on this with all the detail in it, so I can send it to anybody who wants to see it.
Sure, that'd be exciting. That's all on my end.
Okay. And, I was just trying to look up the News Nation stuff. So we've got about 7 minutes left here. And today's kind of a cliffhanger. Shiva Meucci is having serious computer issues. So he may join us. He may be late. So, speak of the devil. There he is right there. Well, do you guys have more questions for Mike McCulloch?
David.
Okay. Hey, I had a question. So when you were testing the galaxies for dark matter, how many galaxies did you check for testing quantized inertia?
153.
Sorry?
153. 153.
Okay. Yeah, because that's the thing. Like, there's so many different types of rotation curves. That I remember doing some dark matter research, and it was surprising. Like, there's a lot that fit into a certain type of model, and then some just fall out of the spectrum and look a little different. So I'm just curious to look. I'll have to look more into how it looked for the outliers as well.
Yeah,
Okay.
I tested disk galaxies, not ellipticals, for example.
Okay, I see.
Because they behave differently.
Yeah.
Okay, and Shiva is here with us.
I am still in a dead rush. I barely got my camera ready. Still trying to find my my presentation. Hopefully my audio is coming through.
Hey, that's Shiva. That's the APEC way. It's complete chaos from beginning to end. That's the way we roll.
I am completely in chaos mode here.
I could take up a few minutes if you need some time to
Could you please? Because I still gotta get my my presentation, my crap presentation I threw together in 10 minutes. I still have to get that up.
Well, and I should ask again. I should do one more call here and see if any of you guys do you guys have questions for Dr. Mike McCulloch. And actually, Harold Tavares in chat asked what is the magnitude of quantized acceleration that QI theory predicts?
Oh, well, the minimum acceleration is 2 times 10 to the minus 10 meters per second per second. So that's the quantum of acceleration, if you like.
I thought of another question, I suppose. Besides testing for thrust, is there any other more subtle way with perhaps like optical gyroscopes or similar lab equipment to detect quantized inertia? Like, I know there's a lot of quantum effects like the, what was it, the anomalous quantum Hall effect or something? Like, a couple of things like that. Or I guess it's not anomalous anymore. They have an explanation. But like, is there like a lab experiment that we could do that would suggest quantized inertia, but we wouldn't be measuring forces applied necessarily?
Yeah, there are several. Nanosphere spinning is a good one. Spin up a nanosphere, and at some point it should start to lose its weight.
Interesting. One interesting paper I had seen from Japan a while back, it mentioned that they had right way spinning versus left way spinning gyroscope, or clockwise versus counterclockwise.
Oh yes, Capacitor.
Yeah, so they on clockwise rotation they saw a loss of weight, and on counterclockwise they didn't see a loss of weight. So that might be something related to quantized inertia. And then on the other,
quantized inertia does
maybe it's different.
The values. Yeah, sorry, go on.
Oh yeah, maybe on the other hemisphere it's different.
Yeah,
it's related
similar
to the
Martin Timar did an experiment like that where he span a superconducting disk, and he found there was an asymmetry in clockwise anti-clockwise rotation.
Yeah,
which is very similar to
that's interesting. Then that agrees with the Japanese paper. That's very interesting.
Yes, and I predict that the Timar result very, very well. And all you'd have to do is do it in the southern hemisphere, and it should be reversed. So
that would be related to like frame dragging or like the gravitomagnetic field of the Earth or something, perhaps.
Well, it's not. That's not the reason for it. It looks like it, but in my scheme, it depends on the relative acceleration of bodies. So if you're rotating something counter to the rotation of the Earth, you get a different effect than if you're rotating it with the acceleration of the Earth.
Interesting.
Spin of the Earth.
So that is predicted by quantized inertia. Then that's fascinating. Very cool.
Yeah.
Awesome. Okay.
All right, I think I'm somewhat a little ready.
Okay, well, why don't we do this? So I think we're probably all set then. Mike, thank you so much for presenting. Thank you so much. And again, so your info is in the notes and your Patreon page. And if you want to drop that into the private chat, I will post that in comments as well. So again, I can't thank you enough. Quantized inertia, I keep hearing about this. I mean, for folks who are following or who watch and replay, like your work is out there and people are discussing it. And I keep hearing references to QI and I keep seeing questions online about it. So you have made a massive impact with your work. It's amazing.
Okay. Thanks so much.
Thank you. Okay, so what I'm going to do now is take everybody out. Okay, and Yeah. So Shiva, we are there. Sorry, and I've been working on stuff. Today's a big news day on the back end, but
Really?
oh yeah. Do you want me to go through it before you get started, or?
I'm kind of curious. What's going on?
Okay. Hold on. Let me close down. What
Let's see, how do I send this presentation up? Also.
Okay, so yeah, I you know what? I'll put this, and I may put this back up later. Share screen. Yeah, I think.
Yeah, ever since I woke up this morning, just computer. I like plugging it and unplugging it, hitting the button. It's just completely dead.
Here we go. So when I'm it's hard to share screen and
okay,
see.
Yeah, I've been watching a lot of this very closely.
Yeah, so this is, let me see, tonight at 8 p.m. So my fingers are crossed. I think probably everybody in our community is interested. One of the things that has been most surprising to me is, it probably shouldn't be, is when I got into like the breakthrough propulsion, emerging propulsion community, you had a lot of people that were talking about warp drives and anti-gravity, and then I connected with a bunch of like the fusion power folks right at the STAFE conference. And so I didn't realize, I mean, I know UFOs have always been a part of this community, but it wasn't until I started doing APEC that I realized that like overwhelming number of people who are interested in breakthrough propulsion are into UFOs.
Yeah,
it should be obvious, but you know, so this is coming up tonight at 5 p.m. The other thing I want to
give a little context that a lot of people might not know about.
Yeah, if it's so. Actually, if it's okay, let me run through. I have a couple more links that I want to put up really quick first. Okay, so this one is. And for anybody who can't wait, and I'll drop the links into chat. So this was Ross Coulthart came on Chris Cuomo. I watched this last night. It's only a 5-minute segment, right? So it's very short, but he does talk about like Jake Barber, I believe, who is this new disclosure person. And they do give a little bit of details about it. So I'll drop that link in there too. It's just additional context. And then very quickly, I'm going to put this one in. I'm going to follow up on this. This is a me thing. I sometimes I think I'm the only person who's interested in this, but basically they are talking about the search for alien megastructures or Dyson spheres in the Milky Way. And this is something that's intriguing to me. Just because of that intersectionality between the singularity, AI, robotics, and space exploration, ET, you know, all of that stuff coming together. So, okay.
Yeah, the search for megastructures is really interesting. But so did you guys know? Okay, so I know Stephen Greer is a very divisive character in the UFO community, and he was talking last year at the end of the year about that a bunch of Green Berets are going to come out in January about UAPs. Then Livelsberger, the guy who blew up the Cybertruck, he actually sent a just in case I don't make it email off. He shot that email off and basically said he knew about UAPs. So that's a very interesting little connection there. And there's something that's been going on here in Vegas that nobody's been talking about, which is specifically that there's a pilot that they just keep saying that this pilot disappeared midair on I think it was the 2nd, and he happened to be an aerospace engineer. Well, my ears perked up, an aerospace engineer from Vegas, given that, you know, we have Bigelow and all of that here. But then I did a little digging, found out he works for General Atomics, very well known for unmanned aerial systems, and his specialty was low observables. So he's a thin films expert on low observables that once worked for General Atomics, which they're across the spectrum, very likely one of the kind of contractors that would have UAP materials. And this guy disappeared. His plane stopped giving data midair on a path kind of in the direction of Area 51. And like I said, nobody's put together this other part of who this guy is. And his disappearance, I don't know what it is. Did he have to be called into like Area 51? Did he get abducted? I don't know, but the fact that he is an expert in thin films tells me he might have been working on metamaterials at some point, which, as we all know, is part of the some of the ideas for how UAPs might instead of creating a huge warp bubble, instead what you do is create at the quantum scale something that's like a warp surface, and then spread that quantum scale out over the whole skin of the aircraft. And so that was how the whole idea of like metamaterials and this sort of propulsion idea would come up. So him literally stopping and being a person who they've been searching for him since he disappeared. His plane disappeared, no wreckage, no anything. So there's a couple of interesting connections, a lot of things going down simultaneously. And then I don't know if you watched that Corbell what's it called? I forget the name of the group that TMZ. They did a special with Jeremy Corbell where he talked about how he gave the that whistleblower that they're talking about. I'm pretty sure it's the same whistleblower that gave the 12-page report that was entered into the record in the last hearing. But what Corbell just came out with yesterday, last night, is basically an accusation that they purposefully lied about who gave them the document. He has all this proof he just put out on this thing that they lied, which endangers the person who came to him and gave him that report, which I'm pretty sure is the guy who's coming out today. It all kind of makes sense that he'd be coming out today to protect his life, because when they said it was Schellenberger who put in the report instead of Corbell, that basically the chain of custody changes, and so therefore the protection then would also change. And it was I really recommend people checking that out, because there was a lot of stuff coming out all at once. And I know Trump promised that he said day one, specifically day one, he was going to tell everybody what was going on with the drones, what was going on with everything. And so I guess we'll see. Some things might be happening really, really soon. So
yeah, this is an interesting year, isn't it? This is starting out,
isn't it? And that's all in January. Man, a lot of stuff here is happening.
in January. I was almost thinking this is like the don't try this at home, and I'm not going to try this either. But they always have people who try and like jump the fence and get into Area 51, and I was like, all you need is a drone. But all you need is a drone, because I think we have if nothing else, we have demonstrated that the U.S. government is apparently powerless to stop drones. So
no, they completely have all the technology they need to stop any conventional drone very easily. I don't know if you've seen those videos where there's like this orb floating and this drone going up to it, and it's like circling it. It gets in close. It just falls out of the sky. You seen that one? That's a really good good video where it's like you got both orbs and actual drones in the same video, and so that's kind of like showing the difference between.
Well, Shiva, it's 2 p.m. So thank you so much for joining us. Let me put your presentation up, from fluid mechanics to alpha. Again, I love your work because there's for me, just based on like what I have read, there is a fluid dynamics basis to it that makes so much sense to me. It's just like it resonates so strongly. So thank you for coming back and presenting more on this.
All right, so I'll try to get into kind of some of the stuff. I'm gonna try to do things a little bit off the cuff, because I literally had to throw this together in like 10 minutes, because I'd been working on finishing off this paper, and then with the computer crash and just a lot of other things, I was way behind. So this you're gonna have to excuse the extremely basic slides, but a little bit of wind up before the pitch. Is basically, so what we're talking about here is I've published some papers, like one of my seminal papers, I suppose, is just basically showing how hydrodynamics is an alternative. It's not just an alternative, actually, interpretation of modern physics. It is fluid dynamics is what gave us modern physics. Maxwell's equations are based upon fluid dynamics, and there are specifics in his papers where there is a rotational element that is easy to miss, I suppose, in the subsequent simplifications given to us by Heaviside. Like you'll see that Maxwell actually went from a vector formalism up to a quaternion paper, but Kelvin talked about how it was quaternions are an unmixed evil. But today in a lot of simulations and things like that, we know that there's a gimbal lock problem that it solves because of the inherent rotational characteristics of being able to use quaternions. And so that's why Maxwell originally did it. And we've kind of lost some of this interlocking of rotation and motion that he explicitly called out, talked about in triplicate in all of his papers that people kind of don't keep up with. So basically, there is this history of fluid dynamics being an absolute necessity. What it is, that math is a descriptive language. It is for describing things. It is not magic. It is a thing that describes. It is a language. And so when you're trying to describe something, you need to make sure you know the difference between the language you use to describe it and the thing that it describes. And if there is a disconnect, then that disconnect can happen, that you don't select the language over the thing that it describes. And that's actually what happens a lot in physics. So going back to the history of it, basically all throughout, up through past the point at which Einstein theoretically got rid of the ether. He didn't. That's in 1920. He says space without ether is unthinkable, for a very good reason. He knew what space-time was. Space-time wasn't new. He specifically said ether, not space-time, because he had just gotten out of he'd just gotten his butt handed to him a little bit by some other physicists in these various conferences, and when it came to some very specific claims about ether, etc., and that's why he wrote this entire long speech to the University of Leiden in response to these various open discussions that were happening in Germany at the time. And so that's space without ether is unthinkable. Then when you track that up through fluid dynamics, you actually find that there's Madelung's equations, where he casts he casts all of quantum physics in hydrodynamic form by using the Wigner-Weil transform, and so once again you have this interchangeability of fluid dynamics with modern physics. But it was kind of, by that point, that was kind of a last gasp of using that sort of approach, and everyone started to go towards fields, which are kind of a hand wavy way of saying what it was that who invented fields, Maxwell. He was actually talking about the stresses, the changes, the things that are happening in a real substance, in a fluid. That's where the field concept comes from, and it's actually kind of been lost that that's what that was, and now we actually just have these numbers that exist in magic space. But there is a fluid, of course, is the basis for all the work that I've been doing and all the papers that I've been publishing over a long period of time. So going from that perspective, let's see, we need to revisit this whole perspective of how do we actually take hydrodynamics and bring it into a point where we're not just casting quantum physics as a in hydrodynamic form, but we're finding some of the things that we've been able to accomplish with our current more abstracted forms. It's like there's not I'm not saying that that what is done in the modern day is wrong. I'm saying the language that they use, the theory, the interpretation, the understanding of what the numbers mean has been completely lost. In other words, they're just moving things around like a computer that doesn't understand the numbers it's given can just crunch the numbers and not know that the numbers actually represent something. And it's like the Chinese room, for instance, is a thought experiment where the idea is you can give a person all of these rules, and they can actually, so long as they get a symbol in, follow the rules, they can put a symbol out, and a person who actually speaks Chinese on the other side of the room will think that they are talking to a person who speaks Chinese, but what they're doing is actually getting kind of canned responses. And this is how the first AI actually worked. And so you can actually use mathematics in that Chinese room sort of way, where you don't know what it is that you're doing, but you are following very specific rules that do create a very internally consistent method of dealing with the subject matter. So in other words, so if your math was good to start with, your rules of dealing with the Chinese symbols that are coming through, if it was good to start with, there are certain ways you can use those rules to create new sentences that you don't actually know what they mean, but they are valid sentences. So that's kind of the same thing. So when we have this disconnect that's been happening over this long period of time, that's where physics can go into a blind dead end hole, because you don't know what the map is not the territory, and you don't know the connection between the map and the territory anymore after you get to a certain level of abstraction. Then also the part of the storyline, going back to the whole UAPs and things of that nature, there is very good reason to believe that since there was this period of time where Einstein was actually kind of fighting against Heisenberg and Bohr on quantum physics. And when you actually look at the history and what was going on at the time, and a very important key to that is understanding that Heisenberg actually stayed, while Bohr ended up defecting. Heisenberg actually stayed part of not just part of, the head of the Nazi nuclear program right until the end of the war. He never tried to defect. He remained the head, researching weapons of mass destruction for the Nazis right up to the end of the war, and was not prosecuted. So why was Heisenberg not prosecuted? My answer is that there is a connection between atomic physics and atomic secrets, and attempting to keep the Nazis from getting the bomb, and ether physics, because some of the things that were happening is as Einstein was continuing forward from that speech in 1920, where 15 years after general relativity, he says space without ether is unthinkable. He starts to work on torsion and things like that, where you basically are treating the space much more like a fluid, much more in a realistic sort of, it's a physical substance sort of manner. And even at the end of that speech, by the way, he says it's not something that moves against itself. However, we know with frame dragging and things of that nature, actually space does appear to move against itself. So he was continuing down that road a little bit further, but he did not like the anti-physicality that was introduced by Bohr and Heisenberg. And I personally believe that what they were doing was saving the world from the Nazis. And there's actually this interesting thing where Einstein is continuing to fight against them right up until Bohr, after his defection, comes to the US, has a secret meeting there's a secret meeting between Bohr and Heisenberg, and there's a secret meeting between Bohr and Einstein. And when Bohr got here, talked to Einstein stopped going, hey, this quantum woo stuff is garbage, I don't like it. He stopped talking about that. Why? Probably because he got on board with not giving the Nazis the bomb and destroying the world, which seems, reasonable to me. So that's just my hypothesis about all of that. So the point here is that I, over the past few months, have put out a number of papers that are in support of the idea of exactly where we kind of have this bifurcation point and how we get back on track when we have these two equivalent sets of interpretations and mathematics, but one side isn't as developed as the other. So in other words, like the hydrodynamic viewpoint is not as developed as others, but there are great people doing a lot of fantastic work on it. Basically, John Bush at MIT, he's working it backwards from the silicon Walker experiments, and the droplet experiments have actually shown all of these various quantum effects can be seen at the macro scale, which means that all of our ideas of randomness underneath the being underneath quantum physics can just be nonsense, and it's an abstraction. In other words, you can treat something that is moving around almost randomly, but eventually has sort of a pattern within that randomness, which that's called chaotic determinism. You can treat that with a stochastic treatment. You can treat it with as though it is random, and thereby using statistics, you can grasp at something that you can't get when it's too detailed, etc. So it is valuable. We will still always have to use treatments of randomness, treatments that treat something like it's random when it's overly complex. In other words, you need to see the pattern of what is a repeating pattern within all of this, random sort of noise. But at the same time, having an understanding that there is a fluid there, that is part of what this program has been about, that I've been working on for the past 20 years. And that is, and now with what I have now done over the past few months, I believe we're finally at a point where I can prove exactly how, where, why. Having this alternative viewpoint advances physics in a fundamental way, grants a completely different and superior understanding of what's below our current physics. In other words, there's just adding an additional layer below, but also still, staying with and validating our current physics work, the wide variety of it. But suddenly we have a perspective where we understand what the language is referring to, what's mechanically happening, that there's a mechanical underlying reality. It's not magic. There is determinism. There is a way in which these systems actually work like machines. So let's see. So talking about the couple of papers leading up to this one, which I'm still in the first slide, is because my slides they're kind of, if we look at the past couple of papers that I put out, basically what I've done is I've provided the two breaking points for quantum physics and for relativistic physics as we understand it. In other words, it's interpretational. What is wrong with our interpretation? What consequences does a faulty interpretation lead to? How can we create an experiment to prove that that interpretation comes to faulty consequences? So I've put out two papers. The first is a paper on looking at the way in which beam steering occurs in phased arrays. I don't know if you're aware of what phased arrays are, but basically you have an array of emitters, so a line of emitters that when the timing that they go off can create the first wavefront, the apparent wave can be shifted in direction, so you can actually steer the angle of the beam using a phased array. Well, the difference, the core difference between Lorentz ether theory and special relativity as interpreted by Minkowski, because this is where we went wrong. Minkowski decided that the one-way speed of light is isotropic instead of the and there's never been any proof of that, by the way. There is absolutely no agreed upon empirical evidence that the one-way speed of light can even be tested. That's the current idea, is that it can't be tested. So by going around that, what I can do is, can you mute that, please? By going around it with this experiment, what I'm doing is I'm pointing out that with the Minkowski interpretation, the difference between Lorentz interpretation, which is still relativistic, there's still time contraction, length contraction, time dilation, and so the various effects of relativity still exist, but there is a mechanical reasoning for why they occur that is underneath. In other words, like the idea of relativity actually gets down to the quantum level of what is occurring to matter when it interacts with space. That's what relativity is in Lorentz ether theory. So the difference that we see is specifically that the idea of relative simultaneity, when you believe that space is specifically, that the speed of light is isotropic in all directions, you believe that relative simultaneity is true. And that means that what one person thinks is simultaneous and another person thinks is simultaneous is going to be different, and theoretically they're both right. This is what leads to the ability to create a wormhole. Like, I don't know if you've heard of the block universe, and the idea is that time already exists, and then if you create a wormhole to a distant place, you could actually go there and back and be able to time travel. And so you have the grandfather paradox, all these sorts of problems that arise from this idea that all stems from relative simultaneity. In other words, that is that there are these different versions of reality that are equivalently true. There are different arrangements of the timing of reality. What this experiment does is it shows that if we change if relative simultaneity is true, and we have a jet coming in at relativistic speeds from the side of the phased array, what will occur is it will change the timing of the specific the firing sequence, which changes the beam steering. And if the beam steering is actually going to some distant object, then basically what you can have is like it's a trigger for a bomb if the beam goes off of it. And what you'll have is a divergent set of circumstances in reality. Now, I'm not saying there isn't relativistic beam aberration. I've got a program that shows regular relativistic beam aberration that always does occur in like a laser beam, etc. That is accounted for. But in addition to that, then once you have beam steering from timing, then what occurs is that a phased array in a relativistic situation would cause a divergent version of reality. So that's the first test that shows that there is an issue with the way in which we interpret special relativity. Now, then the second thing I did is there's a paper right now that is in, it's already gone through peer review. It is now, the editors are still going over the comments from the reviewers in Academia Quantum, and that is the practical design of an Ansible. What is an Ansible? It's an instantaneous communication system at a distance. Now, basically, this is kind of a tongue-in-cheek paper. In other words, the purpose here is to point out an issue in a sort of a cheeky way. Let me take a drink here for just a moment. So in the design of an Ansible, that's a sci-fi concept, comes from, I think maybe from Orson Scott Card, it might have been a different author, that using the fact that entangled particles have an instantaneous effect, theoretically you should be able to, if one can affect the other and you can detect that effect, then you should be able to send information. And now historically, the idea is, well, if you have any kind of instantaneous change, the way in which our current methods work, you'll actually have to have information from the other particle of the pair sent through a conventional means to determine that a change has occurred to your local particle. And that's why we can't currently have what it's called is the no communication theorem. So the idea is, well, even though it's instantaneous, you can't actually prove it, which is awfully convenient, isn't it? That they can never prove that it actually is doing this instantaneous action at a distance. So, I'm sidestepping the whole Bell inequalities. John Stuart Bell tore that apart himself in subsequent books. So I'm just going to, sidestep that for the moment because I'm just talking about this experiment. So the experiment basically uses the ability. We have something called weak measurement, and weak measurement causes a bias in the statistical properties of the local particles, and that bias is something that is entirely locally detectable. So therefore, if we've got something that is entirely locally detectable, it does not require conventional means. So in other words, you don't have to communicate with a particle that is in a distant point. So then you can create entangled pairs using weak measurement, create a bias, and then through strong measurement on one, you should be able to destroy the bias on the second one, and therefore you have a means of instantaneous communication at a distance. So I've either created the design for an actual Ansible and have falsified the no communication theorem, or I've shown that our ideas of instant action at a distance may be flawed in some way. So those two papers are basically experimental bases, I suppose, for what is now this final paper, which it is. I've only just it's still a little bit in development. My most recent version of it I just put out today, an hour ago, and the prior version is available. It's let's see. I will put a link out there for you, but it is basically. Let me try to find the fine structure constant and quantum puzzle sub with classical mechanics. You can find it on ResearchGate, the first version of it. I actually had a problem where I had dimensional inconsistency, and there was also a single claim in there that was that basically it didn't harm the paper overall, but it did not. It was just wrong. So just wrong. But the most recent version of the paper that I just put out today, it's basically a much more refined version of deriving alpha from fluid dynamics. So let's get into this this presentation finally. How long was that? It was 20 minutes. Wow. Okay, I did that pretty fast. All right. So the fine structure constant is around 1/137, and it emerges necessarily from wave mechanics in a physical medium is what the claim is of my program, basically. In other words, so the idea, I think I've got, like I said, I don't know my slides very well. Put them together in 10 minutes, so you'll have to excuse me. So it's not just a calculation, but a complete revolution in physical understanding. We connect fluid mechanics, quantum hydrodynamics, and gravity through a single framework. All right, so the traditional view, alpha, appears mysteriously throughout quantum physics as a coupling constant. Yes, so basically there's something, it's called the coupling constant. We find it all throughout, the way in which atoms behave, from from their spectra to the way in which the strength of their interactions. There's a tremendous amount of ways in which we see alpha playing a role in quantum physics, yet it is simply measured. Nobody knows where it comes from. I do, and it's in my paper. So standard theory offers no explanation, and it has to be measured experimentally, and QED treats it as an unexplained parameter that determines interaction strength. So in the new understanding, alpha represents a unique convergence of mechanical constraints in wave organization. So when waves circulate around vortices in the vacuum medium, geometric necessities force alpha to take its specific value. This isn't arbitrary, but physically necessary, like pi emerging from circle geometry. And then I've got a little, when I was trying to, say it in very short form, it's a key relationship between waves and vortices when both alter the properties of the medium in a way that preserves a spherically harmonic relationship. It's basically a convergence of various mechanical constraints required to accomplish a self-contained machine-like thing. So this is an atom as a machine is what this is. And so the atomic structure, the way in which atomic structure actually plays out, the way in which it occurs, is this idea that going back to Kelvin's idea of the vortex atom, that there is a vortex occurring. But the thing that that I'm adding here that is absolutely crucial is understanding the concept of wave vortex duality. And if you've heard any of my other presentations, this is something I go on about repeatedly. And the idea is that a wave and vortex, waves can pump vortices, and vortices are shed waves. Not only that, if you were to set up for instance, a standing wave in a wave pool that's in a checkerboard pattern, underneath it you will have vortices that are counter-rotating also in a checkerboard pattern. This is because as waves are traveling through each other, how do they not just destroy each other when the peak to trough line up? What happens? How does the wave energy, if the wave itself appears to be destroyed, how does the wave keep going? And I'm talking about in fluids, of course. And because my point here is to point out that there is no difference from waves in media. There's no such thing as a wave without media. So what happens when the wave peak and trough meet and it's completely obliterated? How does the wave reappear? It reappears because it is using the medium itself, properties of the medium, whether it be the potential or the kinetic energy, and so there are changes in elasticity, but there are also changes in rotation. So that's very important. In other words, there's a kinetic energy change that is occurring, and what we see is rotation. So in other words, that's why you can have these waves travel through each other and not destroy each other, because they are transferred temporarily into rotation and then back into the typical form of the wave that we're seeing. So wave vortex duality is very important to understand the idea of an atom as a machine. So what you have is a vortex atom, and then the emergence of electrons is actually kind of what's going to be why alpha is so important. So let me continue forward here. Okay, so basically what we have is an ultra rigid superfluid vacuum that supports both wave propagation and quantized vortices. Now, people in the past have had a problem with the idea of the vacuum being so rigid; it's more rigid than steel. Matter of fact, I'm pretty sure it's orders of magnitude more rigid than steel, which that to most people's minds are like, that's pointless, that's worthless. How could you even work that? The point here has always been, and if you've been keeping up, the idea is matter is an effect more than the cause. The cause is actually the medium. We see the world completely inside out from reality. Reality is that the ether is the thing. It is the thing that is doing stuff. And then the epiphenomena, the phenomena that occur because of the rotations and interactions of that medium, are what we end up seeing as matter. So in other words, you end up seeing these things that where we have electrons that are basically playing the role of cavitations or crystalline defects. So there is these motions, and then the accommodations of those motions at the extremities are compressed down into what we see as material phenomena. So the idea of the vacuum being ultra rigid is it actually makes sense because it is the thing and we are not. In other words, our view of space as being nothing is completely backwards. We are the foam at the edge of the actual ocean. We're just the matter is just what's kicked up from the real thing. Yes, medium's properties change near vortices. This is this is something that's well known in superfluid dynamics. Basically, whenever you have rotational effects in a fluid, it can change the rigidity of that fluid, which then can change the wave speed in that fluid. And that's going to be a very crucial thing to understanding how it is that we can derive alpha from fluid dynamics. So in addition to that, it is absolutely, you cannot do this derivation of alpha without understanding that there is a preferred frame. In other words, preferred frame mechanics are absolutely critical and necessary to be able to derive alpha from first principles. Okay. So in wave-vortex interaction, the waves modify the medium affects the wave speed, and this creates a self-reinforcing patterns. Near vortices, the medium's rigidity decreases according to specific mathematical relationships. The interaction strength, characterized by alpha, emerges from these mutual modifications. So basically what's happening is you have a rotational atom, and it's altering waves, and then there are these kind of feedback loops. It's kind of hard to explain in in physical terms, but basically everything in this model, as you start going through it, now you'll have to excuse me because I'm a bit muddled still from all the development that I've been doing and the stress this morning. But basically you have an interaction where you have to. Okay, the simplest way to put this is you understand that the speed of a ball falling through air is altered by the air that it interacts with, but the air that it interacts with and how it alters the ball's speed is determined by the ball's speed. So there's this feedback loop that we generally use, like partial differential equations and things like that, to be able to explore this sort of feedback loop mechanism. Well, that same sort of thing is necessary in understanding how it is that alpha emerges from a few different interacting properties of the medium when it is both a wave and vortex combined. In other words, so what you have is this atom that is not, it doesn't just have vortexes, but it has waves, and they are interlocked together, and there are specific ways in which they interlock together. So let's go to the next slide here. So I'm not going to get too much into this specifically, but basically one of the problems that I had in my previous paper, like I mentioned, was I had dimensional inconsistency because I basically based everything off of the behaviors of superfluid helium. But the problem is superfluid helium has a rigidity profile, and therefore the size of its quantized vortices that would not be anything near the quantum scale, because it is a macro scale phenomenon, right? And so therefore I eventually was able to find the way to create a scaling factor where we can take the lessons learned from superfluid helium to develop a methodology that works in this framework, which this framework is basically exploring where it is in that nonlinearity starts to occur in the way in which the waves are interacting with the medium. So this is also this term emerges naturally. I'm not going to cover much of that here. It's going to be too complex. So at the quantum radius, basically this is this sort of balance point, and what you're going to find as if you go through the paper, as some of you will, that there is this 1/4 power, and then there's also so you saw the R-4 above there. These two things interact in a way that is necessary. Remember how I said you have to have preferred frame physics? This is the way in which we see the preferred frame physics acting, where you have to separate out these components. So the quantum radius is this point at which it's kind of the balance point at which things change, to put it in a very vague way. And like I said, I'm still working on some documents that I'll be putting out that have all of the various numerical explorations that were required to get here, all of the justifications, because you have to excuse the way in which I've been doing this, which is basically as a programmer, one of the things that you do when you're programming is you work through certain lines of different functions and you get those pieces done. And so sometimes you don't have the whole gestalt of the program that you're creating, even though you know what you're doing and you know you can make it all work together. You have to do one little area of a gargantuan program at a time. And that's kind of where I am right now in this development phase, is that I have been doing individual lines of the code that are necessary to make this derivation work. And it has come together into one cohesive thing. But my mind and the way in which I see the whole gestalt is still a little bit fuzzy. So you'll have to excuse me on that point. So there is this aspect. Let's see. I'm not going to get too much next. That's going to be in the paper as well. So it's basically two times the quantum radius. There's this phase accumulation. Oh, you know what? Okay, so it's kind of gotten too far in here to understand what it is that's going on. So let's go back to the Schrodinger equation. So we know that Schrodinger gave us the way in which we understand electron orbitals, for instance. And so these are these patterns that are extremely directly related to spherical harmonics. And so we end up seeing that our electron orbitals are these spherical harmonic shapes. And what a lot of people don't know is that Schrodinger actually based his seminal work on de Broglie's thesis paper, where he was exploring the way in which you look at two different frames. In other words, he was actually treating relativity in the Lorentz ether theory sort of manner. In other words, he was treating it as a preferred frame theory and not the way in which we're taught today. And so that actually led him to the insights, which then contributed to Schrodinger's development of the Schrodinger equation. Excuse me. So in this model, the basic idea is that there is a necessity for wave closure, and I'm surprised that these I haven't gotten to that in these things yet. Okay, I guess it's talking about it a little bit here. Not enough. No, okay, these slides are crap. So whenever we're talking about the way in which waves are traveling around a sphere, there is a way in which it will not create a spherical harmonic if the wave doesn't close as it travels all the way around. In other words, it does not come back and meet itself perfectly in phase. So because of the fact that there is this issue of needing for the wave to go all the way around and be perfectly in phase with itself when it gets to the other side, and then you have this aspect of rotation of the medium and the alteration of the speed of the wave in the medium, this actually is what leads to the quantization of the orbitals. In other words, there are only specific circumstances, and it's more than one circumstance, that will lead to a stable organization of both the waves and vortices that are present in this version of the atom. Let's see. Okay, hold on. So we covered that basically the not Madelung transform, but so Madelung's equations where he cast quantum physics in hydrodynamic form. I do attempt to connect to that and show the way in which this basically reconnects back with all of quantum physics at that point, so that you can so that anybody who goes in and sort of studies this paper can understand how it's working. Like I said, I'm having to go based on quantum potential as an elastic response. Hold on, I want to get into that. There is a lot here to explain that, like I said, it is difficult to explain exactly how this works. And I just want to give the idea that it is a set of relationships that if you end up doing I've got a couple of programs that are very valuable in that paper. At the end of the paper, you can run the programs and you'll see that it basically shows the interplay of all of the requirements to create this sort of perfect circumstance at different frequencies and at different you've got changes to frequency, changes to amplitude, and like I said, I'm kind of a mess today, so I don't know exactly how to explain something that I'm just barely finishing. But the point here is that with this model, what we can start to understand is the idea of where that there may be a direct link between the refractive index and gravity. So the idea of gravity in this model is basically that there is a general rotation that occurs near matter, because matter is made of rotations, and that rotational field as it goes out away from the the all important quantum radius, then it's going to start to be still present, but not have the same sorts of effects beyond that scale. But the effect is still going to be there, and that effect is going to be that it changes the rigidity of the medium. Changing the rigidity of the medium causes wave speed to change, and this then leads to a sort of buoyancy effect between any kind of particle which has this gravitational effect. And so, in other words, this explains why gravity is present, is that it is a rotational characteristic, a total rotational characteristic of the medium that leads to mild alterations of the medium. Gravity is an extremely weak phenomena, and but it is just these alterations to this gradient as you go away from this rotational structure of the atom that basically leads to gravity itself. And then from there, once we have the fact that we can understand exactly what creates the mechanics for the atom, and basically this wave closure mechanic that allows your discrete quantization and allows you to understand how all of these things interact, then that gives you this perspective on the way in which we may be able to start to manipulate gravity. I haven't developed this much further beyond connecting it with quantum hydrodynamics. And of course, there are all of these other aspects to my other papers, such as my deterministic entropy paper. But this is basically kind of a report of where we stand. And also, here's the thing. A lot of people are going to be skeptical. I'm going to have to put on a second paper that's one of the things I've been running into. Is I've got either this really long set of all of the different steps required to derive alpha versus the derivation itself. And the derivation itself is very small, compact, and that means it's harder to understand because it's too concise. But with it being cleaner, it's easier to understand in another way, if you understand what I mean. And because it's not bogged down with all the historical aspects of the numerical studies that had to be done to achieve certain, finding where to place various borders and basically finding, for instance, the scaling required to actually go from superfluid down to the quantum scale. There's a lot of work that's in the background. So I'll be putting out a second paper that is basically a historical derivation that will take you step by step, and that's where I'll be able to organize my thoughts and be able to understand all that I've done so far a little bit better, because I've just barely finished that, going through and creating all the threads and then seeing them all come together, and then being able to have a single program that's at the end of that paper that shows that you can derive alpha from first principles using fluid dynamics. So I think that is going to be it for me, because there's I will say this: if I am not proven wrong, it's basically pencils down for every other theory, because this provides an underpinning and a greater level of comprehension of what's going on that causes. In other words, this is a deeper causal level that can allow us to understand all of the different effects in physics, and therefore allow us to regain a level of understanding that will allow us to have a greater level of engineering, because it's understanding the way in which the parts actually fit together and what they do that allows you to go from a trial and error. In other words, like evolution creates really complex systems, really valuable systems, and it takes billions of years, and humans do it in a very short period of time. The difference is you can create things in trial and error by banging things together until something sticks, and eventually you'll create really powerful, complex things. And when you do not have an understanding of what the math means, and you do not have good theory, all you can do is go by trial and error. You can bang things together until something sticks, and it eventually will. It just takes many orders of magnitude longer to do so. However, once you have a greater understanding, in other words, when you understand the physical meaning of what the language is describing, what the math is doing, what the mechanics that are underlying these systems, what causes them, the causal chain, once you have that understanding, that's when real engineering can occur, because you know why. And so answering the question why is absolutely crucial, and that's what we'll have here. And so I wanted to present that to you today, and I hope that you all enjoyed it, because it was very difficult for me to get to this point.
Awesome. Shiva, thank you so much. Okay, I'm going to take the slide deck down. I'm going to put the guys up. Let's put our hands together and give an enormous applause to Mr. Shiva Meucci. Shiva, thank you, man. Thank you. And actually, I have Ansible stuff too. When you mention Ansible, that is, I emailed you a bunch, but I'll show some demos too at some point. And I could do that now if you guys want. But let's do questions first. David or Drew, did you guys have questions?
Yeah, I got a question or two. First, Shiva, nice talk, and yeah, it's great to see that you're putting mathematics to your ideas. So I think that's awesome. I was just skimming over your paper, and so are you? It seems like you're trying to get the Bohr radius to come out of this vortex solution, essentially, right?
Yeah. Yep.
And so mathematically, it seems like essentially what you're doing is you're introducing this S quantity, and then you're basically trying to figure out what that should be. So it essentially gives you the Bohr radius and then therefore the fine structure constant. So I guess my question is, in some sense, are you just replacing alpha for S and then saying that you're like solving that, or like because, or is
No,
there some
okay,
way
so
to
if you
figure
see
out what
this,
S is?
Yeah, like I said, there's going to be it's going to be difficult for me to describe my own work here because of the different components and coming at it from different angles. But what we end up finding is that the scaling factor, the S, that is just what's necessary for dimensional consistency. In other words, you can't have a stable vortex and closure of the waves and it be based upon the properties that we see in superfluids. So that was our starting point as a model is what we see in superfluids is because it's got the quantized behavior and that sort of thing. So the S is only playing the role of changing the point at which it will actually create the same circumstances. I'm sorry.
Well, here's another way to ask: if you changed S, would it then change that that Bohr radius?
No. There are just some problems that you end up having. Like, okay, so if you look at my older paper, you'll see there's two versions of the paper there. If you're on ResearchGate, you'll see there where I still have dimensional inconsistency, that the Bohr radius is still present in that paper, even though that paper is dimensionally inconsistent because I haven't solved this problem with the scaling factor. And so that might help you understand the difference there by looking at this previous insufficient paper compared to the more updated one. That might help some. And like I said, there's I am just dead in the center of like I said, I put that out. You see the upload that happened like an hour ago. So there are things that I'm just finally.
Nice. I think I'm looking at the ResearchGate one, but yeah. Anyways, yeah, I can maybe.
Yeah, ResearchGate. Yes, there's two files there. So the one is the fine structure to QHD. That's the newer one, and then the other one is the fine structure constant. And so the fine structure to QHD is the one that introduces the scaling factor. And so that scaling factor is just for making it work at a different scale. It will not work at a
well, that's why I said scale. If you change S, it seems like it would change the scale of the vortex, which would then change the scale of the Bohr radius. That's how I understood it.
Yeah. I mean, I can see what you mean,
and then that would change alpha.
Coming at it from a certain direction, that is absolutely true.
And so all I'm saying is, you're essentially tuning S to get alpha correct in some sense.
Interesting idea, but no, like I said, look at the older paper, and a lot of this. I'm going to answer a lot of these questions in the follow-up. But thank you for pointing that out, because there are going to be things that I need to be able to answer, because everybody's going to try to say, oh, well, this is just fine tuning, or the same problems that any theory runs into, is everybody's going to have some question of whether or not you're just fine tuning. And what you'll see, like for instance, there's two programs there at the end of that paper. The first program is to kind of point out to you how it is that there is this interplay of different components that let's see what it's called here, the Appendix B instead of Appendix A, and what it leads to will show you that there's an interplay of there's an interplay of component factors that are required. In other words, you can't just fine tune down to you can't just use the scaling factor and fine tune down and get alpha. That's just not, it won't work that way. You need all of these different aspects of fluid dynamics for it to work. They're all absolutely critical. I mean, it may look at first glance, it may look like, oh, I can just fine tune it down. It absolutely will not work that way.
I just meant changing the value of S. Like, is S something that is computed, or is it something that is
computed?
assumed?
Yes. Yeah, had to compute it.
It's computed to get the Bohr radius. Is that correct? Or
no, it was.
What's the? Because the paper just states what it is, and then the code also states what it is.
Yes.
In Appendix B, it just sets it as a constant. So yeah, I don't know. Yeah.
Yeah, you'll have to, like I said, you'll have to give me time to work out more explanations of how it gets there, and that is going to be a important part of it. I realize that just deriving it alone is going to leave a lot of physicists with some doubts, and it's like, are you reintroducing the fine structure constant in some backwards way? Is basically the question. I know that's the first question that comes to everybody's mind instantly. It's like, are you just starting with the fine structure constant and injecting it in some way and then getting it back out in that way? And when you once you understand it better, you're going to see that is absolutely not true. There's a requirement of fluid dynamic properties and interactions. There's actually a reliance upon the golden ratio that is there. That is actually very important as well, that I'm not going to describe here. But there is a reliance you'll see there that is absolutely crucial, and because it has to do with polyhedral symmetry. And so there is one of my main sources that I think you'll find interesting is polyhedral symmetry in spherical harmonics. And that was actually kind of a crucial aspect of being able to derive alpha. And that should speak to you, I would think.
Yeah, awesome. Looking forward to seeing more work. Yeah, I'm glad that you're at least trying to put more mathematics to your ideas. I think that's excellent and what is needed.
Awesome. David, thank you. Let me see. So I'll go into comments here.
I think Drew had something that he wanted to ask.
Drew, did
right?
you have a question? Oh,
okay.
And let me see. Gary Hawkins was asking, what is alpha again?
The fine structure constant. It is.
Yeah.
It's something that has been a mystery in physics for a very long time, and it is just a number that we keep testing and finding when it comes to interaction strength, and things of that nature. Whenever we are dealing with anything from atomic spectra to electromagnetic interaction between atoms, alpha just keeps popping up. But nobody has given an answer why it pops up, and this paper gives an answer why it pops up.
And it's also a dimensionless quantity. So if you have any dimensionful quantity, you could always ask, well, why is something 3 meters? And you could say, well, that's, why is it 3? What's so special about 3? Well, 3 isn't special because that depends on the meter stick. But when you have a dimensionless quantity, then it almost feels like it should be more fundamental, So it's like, where does this come from? Especially when it's not just like a mass ratio. Okay, yeah, we could look at the ratio of the proton to the electron and say that's an important quantity, but even more deeply, this fine structure constant, it's really just this dimensionless number. So that made physicists believe that maybe there should be some mathematical calculation for it.
Yeah, because otherwise it's it's somehow it's a constant, and it plays all these various roles, and then it's like, but why? and where does it come from? And so why is this present there? So basically, this is an additional layer of causal explanation. Why is this ratio there, and what role does it play? And specifically from a fluid dynamics perspective, and which specifically uses frame dependent physics, and specifically uses vortex dynamics, then alpha falls out of that.
Hey Shiva, so I got a question for you. This might be a little premature, we can come back to this at a later date, but I'm curious, in even just a qualitative response is fine. Do you have any view on how you would get running of the coupling constant in this fluid picture?
I have to tell you, I don't know what you mean.
Okay, so essentially, at very short distances, it seems like alpha actually changes. So that the alpha that's like the approximately 1/137, that's actually taking at quote unquote infinite distance, but it's still valid very close, up to probably 10 to the minus 10 meters or so. But once you get to maybe 10 to the minus 15 meters, it starts to asymptote. And so in quantum electrodynamics, it's thought that the bare fine structure constant would actually blow up to infinity, which relates to kind of some of the subtle issues with renormalization in quantum electrodynamics. Whereas other people, philosophically, it's thought that there should be some finite bare charge, which is kind of what I think is one of the most interesting problems to try to solve. I am aware there is some work that claims that torsion can be used to get a finite bare charge. And then so they get it running from a finite value to another finite value. And basically the reason why it's a problem for it to be infinite is then it basically says the universe were to require an infinite amount of energy to create a single electron. So it's like if the universe is creating tons of matter, hopefully it's not using an infinite amount of energy to do so. It's like, where would that energy come from? So, but it does, I'm still trying to track this down exactly, like what precise experiments are determining this. Because a lot of the plots you see, they'll just kind of have some rough plot of the scaling. And so it's at least, I was at least taught that there's experimental evidence for this. I still am trying to get to the bottom of precisely what that is. But basically, the fine structure constant is not a constant, is what quantum electrodynamics predicts. So I'd be really curious to figure out what happens at really high energies or short distances with this fluid interpretation.
Yeah, basically what you're the balance point at which the waves can actually go around a sphere at this, like I said, I'm having a very, very hard time translating this into kind of regular terms, because I need to go back through all of my work and re-explain things from the beginning. But it seems like you're kind of hitting on the idea that of what I was trying to say before, is that the idea that the way in which this aspect, this thing that is occurring, which is the change to the medium that is induced by rotation. So it's a change in the rigidity of the medium that induced by the rotational aspect of it, that then it reaches this specific transitional point. And then beyond that, it starts to, it just kind of, fades out. And then that being somehow related to gravity, I think, is probably what you're getting at. And I believe that is also what I'm trying to get at as well, is that this relationship that we see where we're basically kind of above or below a threshold of effects, then that's what that ratio kind of represents, is where that transition point occurs. And so that's the mechanism for creating an electron in this model. I mean, that's where I started from, is the idea that basically we're creating either a cavitation or a crystalline defect, and that's where the electron is coming from, is this sort of cavitation or crystalline defect, depending on how you want to see it. And so and that's why we actually have this phenomenon at the quantum scale, and then it goes out from there. So alpha being a relationship of the change to the medium and how spherical harmonics work in it, I don't know how that would, relate specifically to that same rotational effect creating gravity outside of the atom. In other words, like, because it's a relationship that is required to do this neat thing that basically makes an atom a flywheel, because a flywheel stores energy, right? And so how is it that you can store energy in this sphere? And basically there is that threshold is the point at which the kinetic and potential energy start to shift. And so there's the change to the medium, and then there's the rotational aspect of it. And that's why the superfluid model, you actually have this two fluid sort of perspective that they use. They don't actually believe there's two fluids. There's just two modes of behavior, and that is in the potential energy in the way in which it's altering the medium, and then the kinetic energy that's actually sort of in the rotation. And so because it's a relationship of these things, trying to then say that is gravity in some way, or like how it relates to gravity, it's kind of a difficult, it's a difficult ask to say how that relates to gravity, because I'm simply saying it's the rotation that alters the rigidity, but then the alpha itself relates to the rigidity and so it's both kinetic and potential energy. In other words, there's this relationship of those things, and it also requires wave closure in a sphere. In other words, there's all of these different aspects of what's making alpha be alpha, but it's not. It is specifically the aspect of the fact that the medium can change in the way that we see in superfluids that is leading to how gravity is functioning. In other words, it is an alteration in rigidity of the medium, and it's basically what we're going to see is that the magnetic fields are these basically lines of flux. They're going to be actual vortex filaments. You've heard me talk about this before, that there's going to be vortex filaments that are centers of rotation that are, and the number of vortex filaments that are in the medium are kind of going to be a measure of the total gravity alteration. In other words, the alteration of the medium and the rotational aspect, the number of filaments that are there, how much rotation is occurring, how much the medium is being altered. That's going to be what represents gravity. That is the fluid analog to bent space. In other words, that describes why it is that light bends around gravitational objects. It explains all of those things from this perspective.
Okay, well, on that note, guys, we're at the top of the hour, and Shiva, I want to give you serious credit, because I know you're just kind of like running on the fly with this today. So, but no, it was an amazing presentation, man. So, guys, let's do this. Let's put our hands together one more time for Mr. Shiva Meucci. Let's do some. Let me see. I think Jim, I can provide lab updates for people. But Drew, do you have an update that you want to share with us?
Not really. I spent a whole week with the flu.
Okay, well,
the wind out myself.
So I can do some quick lab updates that I'm aware of, right? And again, everybody, yourself included, Drew, everybody is pushing forward with a ton of projects. And one of the things that's exciting for me is there's so much hands-on work being done right now. So Mark Sokol has been basically recalibrating his dynamic nuclear polarization test apparatus. He is putting in some stuff to reduce noise, essentially. And so he is adding that in. He's going to be redoing some DNP experiments, from what I understand. He did some last year that they took to the ENC conference. If I understand correctly, he is going to be rerunning those experiments, which did produce what appears to be positive results, right? And there were some questions about that. Again, background noise was a possibility. There were some other things that could have, caused errors there. But he is going to be rerunning those with the new machine, more sensitive apparatus, and hopefully noise filtering apparatus that takes things to the next level. So that is where Mark currently is. He has also been working with the connects system, and this is the 3M electrostatic wall. And that's pretty exciting as well. What he said to me the other day was, the revelation that he had was people standing near this are part of the circuit. And so basically, simply by having people move further away from this apparatus, this belt, right? Almost like a giant Van de Graaff generator. By having them move further away from it, it changes the capacitance of the circuit. Apparently the effect gets more pronounced on measuring devices. So that's kind of where that is. Then Curtis Horn and James Woodward, they are running tests. I've been getting emails about that. They continue to run tests. We were trying to get them a vacuum pump, but we did run into some difficulties. But even that notwithstanding, they have a lot of little things that are planned to improve their work. One of the things Curtis had mentioned last year was basically the carriages for that move back and forth. They are doing some design changes on those, and so they're just looking at lots and lots of little refinements to get better and better measurements. And Jim has sent out, I think, 4 or 5 test emails in the last week, so they're continuing to run that. So lots and lots of stuff that's going on. Harry Sprain, who presented, Harry is actually asking me to come down to Tampa. I'm hopefully going to be able to do that. I can't make any promises because it's a pretty chaotic year. And again, we have all of the UFO stuff happening as well. So we have potentially another whistleblower. We have, it's hard to tell, but a lot more going on with that. And arts parts testing continues. I don't want to say anything more there. No revelations or breakthroughs yet, but testing continues on that. So, lots and lots of good stuff. If it's okay, if you guys are you guys cool with it if I show you kind of my Ansible stuff? I'll do a window share here real quick. Okay, so, I'll kind of go where this started from. So you can see this. I'm not going to play the video. I will drop this link into chat. This was an interview that I did with Dr. Tim Maudlin in late 2023. I actually connected with him on a completely different topic. And during the interview, he mentioned this during our first podcast interview. He mentioned faster than light quantum signaling, right? And so my ears perked up and we did a second podcast on it. That's what this is. So Dr. Tim Maudlin on superluminal communication and quantum non-locality. This term here, superluminal communication, that troubles me a little bit because technically it's correct, but another way to express that would be instantaneous communication. And I'll get into that in a bit. So I'm playing this a little bit fast and loose. As you guys are well aware, I am not a physicist. I take things from kind of a Scientific American level, right? So I can find my way around things, but I am not a math person. So, but what he described in that was a fellow named Siddhant Das. I just connected with Siddhant Das. He works at LMU Munich, and he was working with a doctor, and I forgot the gentleman's first name, a Dr. D. Durr, who I believe recently passed away. Das is also working with a team of researchers there. So this is real physics at a real physics university, and they are working on arrival times for electrons and entanglement. And the idea is they believe that they have a method for instantaneous quantum communication that does not violate the no communications theorem. And that is an enormous point because one of the problems, Das expressed this when I talked to him yesterday, one of the problems they run into is most physicists are very well versed that the no communications theorem exists. Depending on their specialization, many of them are just told information can't travel faster than light. from what Doss told me, the no communications theorem actually comes out of a series of specific tests. And at least in his case, what they are working with in terms of arrival time measurements, I believe they said that no Hamiltonian exists there. And so the no communications theorem is silent. This is potentially a loophole, right? He also said that there are several different proposed theories out there, several different hypotheses for arrival times, but none of those has been proven yet. So their research may not just lead to superluminal communications. It may also solve some fundamental physics issues with arrival time measurements. Another thing that he mentioned that was very exciting for me was he said that, and again, I can't see the screen right now while I'm putting this up. Doss said that arrival times are already measured for a number of different experiments. So apparently the theory is lacking, but experimentally this is something that's worked with all the time as a step towards measuring other things. So it's something that is capable of being tested. I also wanted to put up, I'll put this up, Ansible. So this is described as a fictional technology device capable of superluminal or faster than light communication. This idea goes back a long way. There have been different proposed methods for it. I believe Robert Heinlein, back in the old days, had talked about psychic twins as a method of it. Ursula K. Le Guin may have used it as well. Ultraphone and ultrawave are old terms for it. So that's kind of the idea. But the concept is communicating faster than light. And if people are looking for an example of this, this is not a good example. But the one that came to my mind was, can a shadow move faster than light? And for me, and again, I could be mistaken, but for me, I make a distinction between information, which is structure, and a physical property of something, right? So a shadow is information that is encoded into something, and I believe that that is not bound by the no communications theorem. I believe that it is not bound by the speed of light. The speed of light is a limit. I view it as a propagation speed through the quantum foam or the Aether. I view that as a limit on photons. I view it as a limit on particle movement. Information is a meta-property, not a property. So I don't think it is inherently a limitation of structure or ordering unless that structure is encoded into something, right? So a shadow, if it is constructed correctly, can sweep, through a solar system or something faster than the speed of light. The photons in that shadow, of course, are limited by light speed. So for me, I use that as a distinction between structure and physical elements. Now, I could be mistaken, and I would probably get yelled at and beat up for even introducing that. So, again, I will drop links in here.
Without a preferred frame, you actually automatically, that whole sweeping. So in other words, like for instance, you take a laser beam and go from one star to the other, and then once that light finally arrives there, it will appear as though the light travels from here to there. To like say there's a wall, but a wall that's 1,000 light years long or something, and you just sweep the laser beam across it. Then you'll see the laser propagate, but appears to propagate. When you have no preferred frame, the interpretation of what a ray is. In other words, like what is a ray of light? Where in other words, even the angle of incidence, all those things become problematic. I actually have an idea that is our perspective that is, I believe it is possible that there may be scalar waves which could communicate faster than light, but the instantaneous action seen in entanglement, I think, is entirely a problem of mathematical abstraction. In other words, that people aren't understanding what the entanglement means, because we can have that same sort of thing in fluid mechanics, and it's not instant action at a distance. We can have basically it's kind of like, for instance, it is very similar to that aspect of if something has a common source or a common influence, not even common source, a common influence, then like if a light wave comes out and strikes both of them from this angle at their side, then the common influence will make the change that occurs to them seem instantaneously propagated.
Well,
but that's not propagation. It's
yeah, Shiva, let me, if it's okay, I have one more thing. I forgot this, but let me pop this up really quick. I did want to mention this, and again, this is I know this is a little bit different than what you're proposing. It's a similar theme. This is a Scientific American article. I'm going to have to use the back and forward button. Scientific American did an article called Bohmian Rhapsody, and this was in 2021. You guys will have to look it up because it's too small for me to look. It's in the magazine. And so this was on Siddhant Das project, and it does show how they propose their arrival time measurements work. And so there we go, measuring arrival times. Again, this has a couple of different applications. One of those in quantum mechanics is simply to formalize that theory. The other application is hopefully this Ansible, faster than light or instantaneous communications. I did have I had a couple other things I wanted to share really quick. I'll just scroll through that. It's only a 6-page article. So one of them was here, and I will leave it. Maybe I'll leave it here. Measuring arrival times. One of the things was there have been questions about if you can exceed faster than light, right? If you can travel faster than light, if you can send information faster than light, does that violate causality? I don't believe it does, right? Now, in a purely relative universe, if a universe is completely relative, I suppose it's possible. But in our universe, at least I hold that there is a third frame of reference. You could call that quantum foam or Aether or whatever. So the way that I view this is instantaneous communication does not equal back in time. It doesn't mean you can change the past, right? All it means is you can outrun the light cone that emanates from whatever that event is. So that's, again, my physics is rusty at best. I'm not a physicist, but that's kind of my take on it. And then the other thing that I should mention is, so Siddhant Das is working with the university team. Dr. Tim Maudlin is a physicist, and he is president of the John Bell Foundation. So he is just about as versed in no communication as anybody else. I mean, he's the president of the foundation, of the guy who came up with the idea. So that's what I have.
Well, that's the thing. They actually they awarded the 2022 Nobel, I think it was, for having to do with Bell inequalities, but Bell himself completely disagreed with that interpretation. In other words, he, like I said, wrote about how that interpretation of it is ridiculous, especially when we have Bohmian mechanics, as you know, and you say that's Bohmian Rhapsody there. So I think what they're doing is they're trying to use the idea of the pilot wave, but specifically in the Bohmian physics, the idea of the pilot wave is a bit abstract. Whereas what John Bush gives us is an idea of the pilot wave that's much more concrete. Like we can understand, it's not just this one universal wave from somewhere, but it is just the interactions of these various waves and how they can interact. But Bohm specifically had this idea of implicate and explicate order that is very directly tied to holography. So what I was talking about before with that common source, we typically think of a common source sending light directly out to two things, and then we could think of those things as both influenced simultaneously by that common source. And so in a holographic universe, the idea is that that there is this 2D surface, and that all of the 3D objects inside that surface are there because of this 2D surface, or in some interpretations are the 2D surface, whichever. But the point is that and so therefore the instantaneous action is because they're kind of a shared thing in the hologram. In other words, the two, no matter how far away they are a shared thing. But from the perspective of actual, light holography and the way that it works, it's because there are shared sources. In other words, like the waves that bounce off of this, the wave that bounce off that converge at this point, and that creates a new phenomena from that surface. And each point, and each one of those points actually, they all converge at all these different points. In other words, like light that bounces from this, like say this is a surface with a hologram on it. Light that comes off of these 2 points is converging in all of these different places. And the way in which they converge is based upon their angle of incidence. And so it's creating a different phenomena based upon these various convergences, these various points of convergence. And then you just simply wrap that around the idea of a universe. And then the surface is creating all of these different things. And so one area actually represents multiple objects in this 3-dimensional place. And so that's the idea, is how that a holographic universe leads to the idea of entanglement. And I'm not against that, because I actually believe that we have some semblance of a holographic universe occurring, but I think it's like real actual wave interaction, specifically wave interference and convergence, and reliant upon angles of incidence. And so there are these aspects of the way in which the way we make holograms and the way in which they really work, versus holographic universe, which is a bit different. It's based upon some of the same things. But
so let me this is kind of going down, I think this goes down your rabbit hole a little ways, because it kind of goes into the fluid dynamics aspect of it. But one thing that I've wondered about, and I get yelled at every time I ask about this, right? By smart people yell at me, and so I just usually shut up. But Jack Sarfati had this thing a few years ago where he was talking about ER equals EPR, right? And the idea, if I remember correctly, the idea originally was they were looking at black holes and saying, hey, maybe this is similar to entanglement. But, my thought was, does that mean that there's a commonality between entanglement and wormholes? And if that is the case, couldn't some of this instantaneous travel just be shortcuts at the speed? I mean, and you wouldn't have to violate the speed of light.
Right. And my perspective on that exact same thing is that, okay, if we have all these vortex filaments in space where the properties of light may be actually changed right along these vortex filaments in space, and so therefore perhaps, scalar waves are actually traveling at speeds many orders of the speed of light, and so therefore we have superluminal communication being possible. All those things are not really problematic in a preferred frame universe where everything is mechanically operating. You're not going to have it. Time is not a real thing. It is our measure of how much stuff is changing. And why is stuff changing? Because things are interacting, and things are, as things interact, they change. And so time isn't its own thing. And so you don't have this problem with causality. Like Jack Sarfati, he has this retrocausality as part of his work, at least it was 5 years ago. And, he's got this, Beauregard zigzag. It's a bunch of, a bunch of stuff that has to do with time travel. And all that time travel stuff comes from Minkowski's completely non-empirical. There is zero. This is nobody anywhere can prove me wrong about this. It is an absolute fact. There is no empirical reason for conjoining space with time. We have no empirical basis for that, period. It is all fashion, 100 years of fashion, but 120. But in 1907, he added that on. It's a barnacle on top of relativity. And there has never been, you have to be able to separate it from the prior theory that relativity is based on, because it's based upon Lorentz ether theory, which was 100% relativistic, to be able to then take that and say, oh, we can assume that light speed is the same in all directions, when the math was completely the reason the math exists. What the math describes, specifically, the change factor, the way that math works is describing light going different speeds in different directions. That's what it's for, period. That's the only thing that math does, okay? And then to take that math and assume that light goes the same speed in both directions completely separates away from what the math was developed to describe. That's what the language is actually describing, and saying it describes something else. And we have no empirical reason to conjoin space with time, which is the assumption that light travels the same speed regardless of distance. In other words, regardless of direction, instead of it being constant only in a two-way experiment. And so because of that, that's where the whole idea of relative simultaneity comes up. And once you have relative simultaneity, you have to have block universe. And then once you have block universe, then you have time travel. Anytime you send information faster than light, you can send a message back to yourself. in the past. And the only reason that happens is because Minkowski's thing that is non-empirical. And people do keep not connecting this. That's where all the nonsense starts, is at Minkowski.
Let me bring Michael in for a second. And actually, I am going to take a quick restroom break. So I will be back. So we are in open discussion, guys. And, you know, I would say I'll be back in probably about 5 minutes or so.
Oh, I guess I'll just show off what I got if I'm not breaking a. I just jumped in here after.
Oh yeah. Michael, do you want to do like an update for us on what you're working on?
Oh yeah, at the moment, I'm just looking.
Here, hold on. Let me spotlight you. I'll do solo layout.
Look like a mad scientist here a little bit. I'm making LK99 and similar things. There's also a hydride-based superconductor that I'm working on. There's well, so I don't know if it's a superconductor, but basically there's something called a nonohydridorenate ion. That's rhenium with 9 hydrogens attached to it, and that's stable at standard temperature and pressure, well, relatively stable at least. And so people have synthesized lithium, sodium, and potassium nonohydridorenate. And so I'm gonna give it a try and synthesize maybe ammonium nonohydridorenate, and then a bunch of rare earth nonohydridorenates, and we'll see where that goes. I mean, just in terms of the basic science, it's an interesting thing. And then the ratios for the hydrogen to other atoms on all of these compounds it's ridiculous. So, like there's erbium hydride and rare earth hydrides, and those are more dense, I guess. But I mean, these would be good candidates for room temperature superconductors outside of the usual. Yeah, I mean, that's the main thing. And then what else we're doing? Yeah, we're just making a bunch of LK99 variants and seeing if anything works. We're trying to use phosphate, silicate, and borate ions instead of just phosphate, playing around with things. And now I'm spotlighted, and hopefully Tim's back soon. I've run out of things to say. Let's see what else we got here.
Oh no, you're spotlighted. You got to talk, man.
Oh no.
Keep it going.
Yeah, well, okay. So side project here that I had. I think I probably mentioned this before, but oh, now my computer's going slow. Can everyone hear me?
You're coming through.
Okay, maybe I'll. Okay, yeah, okay, it's good. It's real time again. So aluminum, antimony, concrete. No CO2 involved. So that is based off of the mineral bahianite, which I have my suspicions is from an old terraforming probe from 2 billion years ago that introduced photosynthetic life to Earth. That's a long story for another day, but the concrete is as hard as sapphires. It's a hardness of 9 on the Mohs scale. The challenge I'm having at the moment is getting just the right mixtures of salt. Basically, there's chlorides and nitrates and things. But yeah, getting the right ratios of everything to have a compact concrete. Right now, it's a bit porous. So the individual crystals are hard, but the overall material is chalky. And so there's a couple different things we're trying to improve that. But yeah, I have cut glass with this stuff. It's cool. I mean, even just as like cheap, ultra hard polishing compound, it might have its uses. Anyway.
Well, no, Michael, that's awesome. You are my materials guy. Michael is everybody's materials guy. That's the problem. He's getting spread too thin.
Oh, so. And there was that one fellow who dropped us the sample, the aluminum sample from the bounce site near Roswell, I think. We'll be getting that tested tomorrow. Finally, took forever to. My friend who's got.
Can you do me a favor? When you get that tested, can you get a copy of all the data over to Jared?
Yeah, we can do that. I got to ask him. He probably still has the old data that we got from a previous test on other materials. Like we tested some carbonado diamonds from near where the bahianite is from, that we suspected were of artificial origin, and we found acicular grains of titanium and vanadium and stuff inside them, which suggests like basically those are nitrogen getters at high temperature. So if you wanted to sinter diamond and you didn't want nitrogen being involved, you would add those sorts of powders, and they also reinforce diamond structures. So anyway, yeah, those carbonado diamonds in Brazil and the bahianite samples, those are quite anomalous, I think, worth more study.
By bounce site, do you mean like that video where the UFO comes in at an angle and then like comes out and like shatters, or like bounces twice? I remember.
Yeah, the guy who got the sample would know more than I do about that, like the historical stuff there. But I believe so, something like that. Yeah.
Yeah, and actually, if it's okay, since we're and again, I have been bound to secrecy. I don't have anything super interesting to share on that, but I'm not supposed to share arts parts updates. But what I will do is put up a copy of Jared's user list. I believe he is Mighty Brain, and I think he is in UFOB, and so I'm going to put that up.
Yeah, he's moving mountains, getting data on all the samples. It's really impressive.
So yeah, that was why I wanted to share that. Jared is like the amount of emails and chats and messages. I mean, he like, I swear to God, he's like hitting the bottom of the internet, you know, like stuff that like, you're talking like 1990s buried. It's like, where did you find that? So what I'm going to do is, I'll just put Jared Yates on Reddit, and then I will let people look at what he's posted there, because he is just, you know, studies and all sorts of stuff. He found
he's just using the
study.
Wayback Machine and going all the way to the beginning. Just going through the internet there.
Yeah, I keep asking him, I'm like, dude, you got to back this stuff up. Like, you give it a year and you won't remember what you have, you know? So.
Yeah, there needs to be a database, preferably public, but I guess some people are working on private company stuff, so you got to do what you can.
Well, we may learn more about that in like an hour and a half. We have this Newsmax thing coming out.
It's going to be just an hour and a half. I'm looking forward to it. Is it the same? Is it the same whistleblower that wrote that 12-page report that they said was 11 pages, and then added on?
I think this is a new guy. And I don't have that story up anymore. I've never heard of this person before. So
yeah, no, his name never came out. There was an unnamed source from Michael Schellenberger. Like they introduced it as Michael Schellenberger has put this into the record during that congressional hearing. But in fact, you can see. I've forgotten his name suddenly. The other fellow who actually was the one who actually did add it. He had so much proof of it. He even had Schellenberger on the phone saying, "Yeah, I don't know why they said that I did it." And so it was so weird. And so that's like that whistleblower kind of was like his protection's up in the air, since he literally was walked into people's offices. In other words, he pretended to be part of the camera crew, and they walked him into congressional offices to have meetings. And yeah.
So if I don't think he lists his name here.
Constellation.
I asked, I've been asking around, and I'm going to try and do a podcast with Larry Hancock. I'm not sure if that name rings a bell, right? He's not as public as a lot of folks are, but he is an amazing UFO and defense researcher, and his knowledge, his history goes way, way, way back. And so he emailed me back about the Chris Como article, the Chris Como video. And he said, one of the things that I'll just read what he said. One of the things that drew my attention was brief mention that this individual and his evidence relate to recovery of objects from the range, which would generally apply to a test range, suggesting that NHI were crashing on a military test range, or these objects were crashes related to NHI devices being tested. And so the word retrieval is interesting in that context. He also said it would be interesting to see how visual evidence confirms it. And so that's the majority of kind of what he wrote. The other thing I've heard in the Chris Cuomo, that 5-minute clip from last night, I believe that this individual has already presented his evidence to the Senate Intelligence Committee. Ross Coulthart said he was with him when the guy did that. And supposedly they're going to be playing a brief video of crash recovery tonight. So,
oh wow, that's great. Yeah, I bet it's the same Immaculate Constellation guy. I don't know if you guys kept up with that whole thing when it got released. Schellenberger is actually who popularized. He wrote an article about Immaculate Constellation, which was they finally found the actual name of the recovery program. And that's the name of it. I did a Google Trends search, and there's all these spikes of Immaculate Constellation, UFO, things like that. People are searching for it before anybody had ever heard it before. In other words, it was, and all of the searches initially, people who first started doing this, looking at Google Trends to find out if anybody had looked for these words, you could see that it was all at points at which something major had happened in UFO news, and the searchers were people near military bases and things like that. So in other words, they were searching to see if anybody on the net had gotten wind of Immaculate Constellation. Nobody had heard of Immaculate Constellation before. I guess it was, I think, October of last year, maybe. Nobody had heard those words said. You don't see anything but a few of these spikes, and their search is coming from intelligence agency locations.
okay, sorry about that. Messages coming in. So yeah, it's interesting. It's interesting. So David and Drew are being quiet. I don't know, but they're still with us. They haven't left and discussed yet. But
I called Drew earlier in the week, but he was sick. Are you doing better, Drew?
Yeah, and I had one of the influenzas. Just out, took me out for 7 days.
Oh, that's tough.
It's this one's a bear. I mean, I haven't had the flu in 20 years. This one killed me.
Ooh.
But I survived. The reason I'm quiet is because I never understand anything Shiva talks about, and I really am interested because this that 1/137 thing shows up in our propulsion math, and I have no idea where Charlie got it from or why he needs it, but it was fundamental to producing the correct amount of thrust from the equations. So, are you ever going to get a Dick and Jane version of what you were talking about today?
Actually, one of the things I do is I've been running things. There's this podcast, the AI podcast generator. They do such an unbelievably good job of breaking down topics into like layman's terms and talking about it. So there is I generate podcasts off of my papers now, and so that people can listen through them. I put them on my channel. My older paper actually has a podcast that you could listen to that might explain it better than I do, because it's unbelievable how well how good of a job it does in explaining these topics.
oh, there's Brendan. Brendan appeared.
Hey,
Wild Brendan appears.
Yeah,
How's it going,
sorry,
folks?
it popped you up at the bottom of the screen. I just scroll down. Yeah, welcome.
Hey, no, it's all good.
So I was
just
going to
been
see
enjoying
if
the
Brendan
show.
wanted to moderate the APEC open mic. I've been talking with Brendan about that, and then I would still be here at least for a while, at least at the start. And the other thing that we talked about was maybe not recording the open mic. We could, maybe not. I don't know. But then having Brendan moderate it, and part of that is because I'm so used to doing these webinars that I'm kind of stiff for that open mic format. That was supposed to be just long form open discussion, and the problem is like I'm trying to turn it into something it's not. So we have to redo
I'm open to that, and we can talk about that in the next couple of weeks and set it up if that's the way we want to go. Obviously,
yeah, we have time to figure it out.
Things are usually up in the air for me here, but I have experience helping moderate like open Zoom discussions for the nonprofit that I work for normally, and so professionally speaking, I'd be up for the challenge. Practically speaking, we'll just roll with it and see what happens.
Yeah, this year is just, it's starting out crazy, but
yeah, but it's exciting. I just had a couple of days ago, I had a talk with our friend Jason Cassabri. and revisiting his
awesome.
dielectrophoresis work, and that was really fascinating. And he taught me a lot about fusion, and that, I guess, his bread and butter is fusion, and that was really exciting. And as far as media goes, I was really blown away. But I don't know if you guys are following this Ecosystemic Futures podcast on Apple and Spotify. Oh my God, it's great, and it's everything we're into. They've had Travis Taylor, Hal Puthoff, a few big names we're familiar with. But
I
this
wish
episode,
they had more specificity with what they were talking about. But yeah, it was.
Yeah, I think some of these guys, they're under NDAs. Obviously, they're not allowed to like explicitly talk about all their work. But there was a guy, I think, last name Lentz, that was talking about
Eric Lentz, probably.
Yeah, it might have been Eric Lentz. They're using gravity waves to increase the power of transmissions, to send high energy transmissions, to get them to Mars and stuff sooner. And that's just freaking amazing. But what just occurred to me is like a lot of this is going more mainstream, and we don't have to look over our shoulders, for potential attackers as much.
And there are some incredible things were happening, even like with NASA. I mean, the fact that this solar probe that they have, the two things that, what was it? One of them was the solar probe. I can't remember the name of it. It is actually in the sun's atmosphere. It is that close to the sun, technically. So NASA has a probe, I believe it's still up there right now, that's so close to the sun, it's actually technically in the outer solar atmosphere. To me, that's amazing. The other thing, I did a podcast with Avi Loeb maybe 3 or 4 weeks ago now, and he said he did the calculations. I think this was Hubble or James Webb. I think it's Hubble. He was saying that you could see the city lights on Earth from Pluto with it. And the thing is, James Webb is going to be succeeded by the Roman telescope in a couple of years. And then in the mid-2040s, they're going to have the Habitable Worlds telescope that replaces Webb, and that replaces Roman. So Roman is supposed to be used for spotting exoplanets that they think have life, and then Habitable Worlds is going to take that catalog, I believe, and focus in on them. And that's using conventional technology, right? But like, we're stretching the limits, and it's getting so much better. This is just really amazing stuff.
You're getting better at improving that signal to noise ratio with computing and stuff too. So a lot of that is filtering, and hopefully we don't overuse AI in that, because we don't want it to hallucinate things. I think there might be some, like, Breakthrough Listen was using AI to try and discern potential signals from like Proxima Centauri, for example, and there's been a couple of false positives that may have been based on hallucination. But yeah, it's exciting stuff, like things that I saw in documentaries when I was a kid finally becoming reality, and that's awesome.
Yeah, and that's conventional. Those are pretty conventional technologies, and it's like, okay, if that's what we can do with that, then what can we do by stepping outside of the mainstream? What are those things that are out there that have just been neglected or prematurely ruled out? So
the low-hanging fruit, so to speak. Yeah. And I think, even the unconventional, though, is starting to become more widely accepted. I think even it was a little suspicious, but like on this Ecosystemic Futures podcast, they had NASA, they had DOE, they had Small Business Administration, they had a number of names of organizations that are all sort of lining up, and the main conversation was about how do we get funding to normal people that are interested in this, that want to push these things further. This should be interesting to everybody here, because money, right, to power your operations. But the people that run things in this country are starting to get serious about wanting to make sure we stay ahead of the game, and that's really exciting.
I hope so, but we should remain vigilant just in case. There've been enough false starts to this whole thing.
Absolutely. Yeah.
Well, and speaking of vigilance, I want to, I won't dwell on it, but I want to bring things back to the security thing. So this is again something I've been doing podcasts on. You know, I mean, there are so many people who are spying on our private communications that I'm not sure who to complain at first. But my assumption is the NSA sees pretty much everything, so I'm not even worried about them, you know. But there was this thing about Russia has infiltrated all of our telco networks, and China has infiltrated, I mean, like TikTok and, you know, several other things like that. So I've been doing a series of podcasts on that. Most of the folks that I know who are privacy minded are going to the Signal Messenger. Signal seems to be the one that everybody is using these days. And I was told, I've been told, that Google is very good on security. I interviewed a security expert with DoD last week, and he said, in general terms, yes, but he said, really, you should probably be using Proton Mail, you know? And again, I view myself as kind of, and you guys are all probably in the same boat, right? I mean, I exchange emails with you guys. I'm of two minds because it's like I don't do anything worth hiding, number one, but number two, every now and then, you know, I get my knickers in a bunch, and I'm like, I want my damn privacy. So,
I think the hardcore one is security enhanced Linux, either 4 or 5, and there's probably a 6 by now. But security enhanced Linux has a mathematical proof that it's not hackable as long as it has certain hardware under certain conditions. And so, yeah, security enhanced Linux, that's the only problem is it has no drivers for anything. So good luck. And then you have to write your own drivers, and then is that going to be secure?
yeah,
Did I ever tell you about the one security scare I had? So, like, for instance, way back, you know, before 9/11, I was researching ring laser gyroscopes, and I was talking to Honeywell about it because they're a DoD contractor for, you know, for that kind of technology, IFOGs, et cetera. And I was asking them to, you know, they had scrubbed the internet of a bunch of information that was freely available before 9/11, and I was calling them up trying to get that information. I guess this was just after maybe, and so they said that they had to report me to the Department of Homeland Security for just for asking for it, and I was fine with that. But then a few years later, and I don't know if you remember the era of when we were just all like replacing our computers regularly, and you had to just like move all your data into a backup, and so you had a backup of a backup of a backup, and you had like layers of backup sitting in on your drive. Well, I had actually moved on and was really doing more in neuroscience research for, you know, a few years. This was many years later, and I'm sitting there. So there's no reason for me to ever even touch what's in the backup drive. I am not touching the keyboard at all. And a document that's a NATO document that may have been reclassified, because that's one of the things that happens. They reclassify them on ring laser gyroscopes, pops up on my computer. It just was accessed and brought up in front of me while I'm not even touching it. There's no accidental way for me to have, you know, in any way. I didn't even remember I had that document. And this was at the same time that they were actually like investigating a friend of mine because he'd done the horrible sin of raising mushrooms to treat his own depression. But so that was I've had a security scare once that was like, I was like, I don't know if that document is still unclassified or not. I got it through normal means, guys. It's like it was just available on the internet back before 9/11.
So
yeah.
was that, out of curiosity, was that on Linux or Windows?
That was on Windows.
I left Windows.
There you go.
I went Mac in 2015. I went Mac, and there were a few different reasons for that, right? But the security thing in Windows, I've never felt good about security, and my primary concern is identity theft, right? Folks who steal your, because I know folks who've been, not just that, but social media theft as well. I mean, so pretty run-of-the-mill stuff that all of us should worry about. And honestly, for me, those are my primary security concerns are stuff like people who want to steal your bank account info, right? that's because there are lots and lots of them out there.
And the thing that worries me is like organized crime and illegal parts of the government and things like, I still don't know if I trust the story about Mark McCandlish personally. Like, I don't know what happened to him, but Boeing did off a few other whistleblowers recently.
So Mark, I talked to a very close friend. He was in our conference, right? And he kind of went silent for a couple of months. And I was wondering as well, right? And I talked to a close friend of his that I trust, and they said, especially towards the end, but they said this is a man who slept with a pistol under his pillow and drank himself to sleep. And they said they weren't surprised in the slightest. But I think I think that is important, and it's overlooked. Is bad things can happen to good people, and it doesn't have to be a conspiracy, right? I mean, and so when people are struggling, reach out.
You can have paranoia and people being attacked by the system can run hand in hand with suicide. Look at Aaron Swartz, for example, the kid that was, again, talk about people being prosecuted for confidential documents and stuff. He was called on the carpet, basically had the book thrown at him, and he to avoid life in prison, he unalived himself to simplify matters, and that was really tragic. But something like that could have happened with our friend Mark. Just won't know exactly.
Yeah.
And his only sin was wanting information to be free. He just didn't want journals to stifle science. That's all he wanted.
And publicly funded universities at that too. Our own public tax dollars actually go to free science that wasn't going to get bought up.
He was a hero.
I'm not going to say, I'm not going to make any, I don't know what you'd call it, sweeping comments about this or that conspiracy does or doesn't exist. But what I would say is that I have known several people that have committed suicide. And one of the struggles that goes I think this goes unacknowledged, and I think it's really important. If someone takes their own life, this is just my thought. If someone takes their own life, it's really easy to point a finger and say, "Oh, the government did this," or the Men in Black did that. But like, doesn't that ignore, like, in the cases that I know, these were intelligent people who felt like they didn't fit in. They had a small group of people that they understood, and when they were having trouble, the people close to them, myself included, didn't understand, and the part that troubles me is, like, again, rather than looking at conspiracies, I think one of the things that we need to do is be more supportive of each other. That's where
don't minimize the amount of pain that some of these people who are isolated by events can be going through. I wasn't saying that I believe that he was directly killed by them. I mean that the pressure that they put on him. I had a best friend who, like I said before, that same guy that I was talking about who was investigated, all he did is grow some personal mushrooms. He wasn't selling to anybody. He was just growing them to try to deal with his own depression. And then they threatened him with 30 years in prison for just doing that. And basically that caused his mesothelioma to flare up, even when his father, who worked in the same stuff, didn't have any of it, and that killed him. So in my mind, they killed him for just trying to make his own life better. And so that's all I meant, is that you can pressure people so badly that they feel so disconnected from society, so hated by community, which is so critical to all of our existence, that the pain is too much for them. And they can actually, their immune system can fail, even if they don't off themselves. You can kill them just through the absolute horror of being just not part of humanity.
So then the other thing that I should, and this is kind of not counter, but this is kind of an aside, is if you look up the statistics, I had a friend who committed suicide several years ago. The number one statistic in the United States is like males over 40. I think I think they've called it an undiagnosed epidemic, right? And there are a lot of cultural factors that are at play there, but that's just something to be aware of, And there are some cases where, Like I had a close friend who lost his wife to cancer, and he just couldn't adjust and took his own life. And in that case, I don't think that there was anything anyone could have done. You know.
Well,
So
but then
sometimes
on
you
the
gotta
flip side of that, like other people have received like threats. Like even like I think David Grush mentioned some threats he received. Like he had to file a complaint for retributions or whatever. Or no, it's like retaliation or what? Yeah, retaliation, and like stuff like that also does happen. So like, and not just David. I've heard from other people too who like were threatened. At some point, I've had a bullet placed in my apartment too. At some like, I don't know. That was weird.
Yeah, let's not pretend extrajudicial killings don't occur.
Yeah, and that was like before even most of the APEC stuff. I was looking into some things
the
before they
Boeing
were
thing.
allowed, I guess.
Yeah, the Boeing thing kind of got me, right? And if I remember right, didn't that guy leave a note? I think he left a note for his wife that said, "If I end up dead, it's not an accident," you know? And
Yeah.
and then there's this thing that I don't even think it's hit mainstream news yet, but about the was it the OpenAI researcher? who
Yeah,
just committed
that.
suicide?
Yeah, that doesn't smell right either. That one.
Yeah.
I'm sorry, if you look into the Livelsberger exploding himself, did he explode himself first or did he shoot himself first, theoretically? You know, it's like
It's entirely possible he could have been killed beforehand and somebody else drove the Cybertruck there remotely. That's
yeah,
another...
and so there's some the fact that he was contacting people saying, in case I don't make it, and giving them Dead Man Switch, which then came out. Yeah, it doesn't look right either. It really doesn't smell right.
Yeah, it's like he wasn't. Yeah, he was. Oh, anyway, to change the subject from these dark matters, Drew, I've got some of the stuff.
We gotta get rid of the dark energy.
Just made it. It's a little dirty. Got to clean it up, but yeah, we can make diamond aerogel maybe. I'll see. I'll have to figure out how to cross-link it, but should be able to make a gel and then diamond aerogel. Ooh, something in my eyes.
And that actually that is exciting because Michael, you do have amazing material skills, and so
yeah, I don't even know how.
It's amazing to see if you can fill
the first
in.
one to be able to recreate the technology of the ancients and create giant granite monoliths. You're just going to just start pouring them like concrete.
Hey, when you say diamond aerogel, are you talking about like carbon foam, carbon aerogel?
Well, diamond like carbon as aerogel.
So basically, it's a carbon foam. I mean,
Not just
it
carbon though. It's SP.
It looks like something black floating in that liquid.
It's tetrahedral oriented instead of flat like graphite. SP2 hybridized, I think. But anyway, it's an insulator.
So let's say it works, and you make a box of it.
Sure.
Stuff looks like a piece of black foam.
Yeah. Not sure what the conductivity is. We'll have to test it.
My thought would be, I mean, if we're going down this road, my thought would be for Drew, right, to come up with a list of like stuff I'd really like to have, and then just get that over to Michael and be like, "Can you make this?"
Oh yeah, I can make all sorts of. There's, in fact, I have my suspicions that it should be possible to isolate, based on Thomas Townsend Brown's notes. He mentions that specific isotopes and specific chemicals are better electrogravitically, and if you can, that opens up the possibility of using electrogravitics to separate electrogravitically active isotopes, which could be very interesting. Yeah.
Yeah, having people.
Were you talking about how bismuth was one of those substances that the dielectric constant can change based on how you charge it?
No. He was somewhere in his notes. He was mentioning ball milling tantalum powders and tantalum oxide powders, and then electrostatically separating some of the tantalum, and that tantalum was more active than the other tantalum oxide. But there's better ways to do it, I think, than what he did. In fact. So that might be exciting.
Awesome.
Yeah.
Then
guys-
you embed those in your dielectric substance or in your sculpey clay or your foam or whatever you're working with. Or...
Yeah, presumably.
We're just about at the top of the hour. We can keep going if you like, or we could close things down for the day. We didn't really have a lot of lab updates. That's why it's running a little shorter, and that's totally okay.
Yeah, I mean, all I was, I just briefly went over making the LK99 hydroxyapatite using various metal nitrates.
Okay.
And then, yeah, I already discussed that though, I guess.
Well, yeah. Why don't we do that then? So why don't we call it a day? That gives us about an hour before the big Newsmax announcement,
Nice.
and we will see how things go.
I'll probably just keep working until that. Yeah.
Yeah. Okay. Well, guys, thank you. This has been APEC for Saturday, January 18th, 2025. First one of the year. This has been an amazing conference. So thank all of you. Thank all of you. And thank you to everybody who is attending virtually on our wide array of channels. So
Thank you, Tim.
Yeah, thanks.
Thanks a lot, Tim.
Always fun.
Thanks, Tim.